Good morning, Amitava.
Amitava, good morning.
Oh, good morning. I'm sorry I was muted and I didn't realize it.
That happens to all of us
Good
all the
morning
time.
to all of you. And as I said, I'm reporting for duty.
Yeah. What do we have? We have 28 participants. Should we wait a few more minutes? I think probably 2 people are waiting still to get in. We're getting close.
Amitava,
Yes.
your room looks like the library I grew up in my father's house. After moving to this place, in 2008, my books are still in boxes.
Is that right? So let me tell you, I wish I could claim to be as erudite as the bookshelves behind me suggest. My wife is a feminist scholar. She owns 3 shelves of those books.
Oh, man.
And it's the history of feminism, really. She's picked up books from all over the place. We are both
Yeah, I know exactly what it is.
Yes, and it's gotten to be totally out of hand. I have a pretty good collection too, but nothing compared with hers. And that's what you're seeing in the background.
I'm impressed, yeah.
Yeah, I can't pretend to you I know what is in those books. I pick up a few things from her when we talk.
Yeah, it's really nice. The whole background is really nice.
Well, thank you. I like to work in the basement for that reason. Makes me feel like
there's something cultural about it too.
Yes, that's true.
Bengalis are like that. Growing up in India, we had hardly any furniture, and we traveled right from Calcutta to Bombay to Delhi, and our furniture were our books.
Exactly.
And mother would get so upset.
Still remember. True. Yes.
So I'm waiting for orders on when to begin.
Yeah, I am waiting to give those orders. I think I will be your moderator, Amitava.
Okay.
So, and I'm just waiting to see the number. It's at 35, so I think that may be about as high as we can expect it. Maybe a few more people will join in the next 10 or 15 minutes. But so I'll just turn it right over to Amitava, who's going to tell us about particle acceleration, right?
Yes, I will. Thank you. And should I share screen?
You should. Yes, anytime you're ready. Let's just start right off.
Can you see my screen?
I can. It's in the presenter mode right now. Now it's, yep, appears, maybe, well, no, sorry, it's not cut off.
I would like to see the bar moved. Let me see. The bar is getting in my way.
Oh, yeah, that is a problem. That is only on your screen, though. Yeah, don't worry about, I mean, we're not seeing that, but
okay.
You, if it annoys you, you might move it around. You can minimize it, etc.
Yeah.
Oh wait, am I okay?
All right. Now, all of you can see my screen. Dana announced the title as particle acceleration, and that is what I thought I would call this lecture. And then this is a common dilemma that I have. Particle acceleration is sometimes meant to exclude considerations of particle heating. Both are processes of energization of particles. So I substituted the word energization for acceleration. And I'd like you to keep in mind that the title encompasses both types of phenomena. As for myself, as you all know, I teach in the Department of Astrophysical Sciences at Princeton University. and also serve as the head of the theory department of the Princeton Plasma Physics Laboratory. It's been my pleasure and privilege to be associated with this summer school for a fairly long time. And we have built on the shoulder of giants, as you know, and two people in particular, Karel Schrijver and George Sisko. You would have met one of them had it not been for personal developments at Dr. Schrijver's end. But his spirit pervades this school. And in particular, as you have heard already from Nick and others, we did recommend that chapter 8 in Karel Schrijver's Principle of Heliophysics book is one that I hope you've had a chance to just quickly look through, especially sections 8.1 through 8.4. In preparing this lecture, I am talking about things that are not my expertise, subjects of which I am a student like you. And I found a number of lectures, some of which are available on our summer school website, very useful. And those are lectures by Ben Chandran and Marty Lee, who have in the past been lecturers. But I also went into the astrophysics literature and found lectures by Blasi and Ellison. Ellison actually is very interesting in that he straddled both the heliophysics and the astrophysics community and wrote some good review papers that have been very useful to both groups over the years. So I have borrowed from them liberally with attributions wherever possible. So let me tell you what I'm going to try to do. First of all, Dana is keeping track of raised hands, and I appreciate Dana's doing that.
I am. Yep.
And so at any point, if any of you want to ask a question, please stop me. And Dana will tell me when there is a raised hand, because I'm looking at the slides and I'm not being able to monitor it at the same time. And I shall stop as soon as I know about a raised hand. But I've also interspersed a couple of question slides which weren't posted with the slides that were posted last night for obvious reasons, because I didn't want to tell you what my questions are going to be, in which I hope you will participate. I wish I had the time to prepare even more slides like that, but we'll do the best we can. So with that bit of an introduction, let me move on to the second. Oh, that's great. I immediately managed to stop sharing. I don't know why. Okay.
Oh. Okay, we're back.
Okay, this is the arrow.
Yeah.
I want to remind you, just to set context, that the first lecture of this summer school, Bill Motag actually pointed out that there are some drivers of space weather, and that these refer to variable conditions on the sun and in space that can influence performance and reliability of space and ground-based technological systems, and even in some extreme cases endanger life or health. And he divided the problem into three scales: the R scale, the S scale, and the G scale. And energetic charged particles is what was called the S scale. Today's lecture is about energetic charged particles. It undoubtedly involves magnetic fields, the G scale, when it comes to heliophysics systems. It also involves radiation, and there'll be less conversation about that today, even though keep in mind that that there are lots of implications for energetic charged particles as far as radiation is concerned, and I'm spending less time on that today, though I shall mention it. And there's just, particularly when it comes to astrophysics, there are enormous consequences for all kinds of radiation and their properties that I won't have the time to go into in depth. So let me emphasize right away, and this perhaps reflects my bias. I'm trained as a plasma physicist, and I have learned space physics and astrophysics from practitioners of the art. And that journey began many years ago after I finished my graduate studies. And it's been a learning curve, and it continues to be so. So there is definitely a underlying plasma physics bias, if you will, in these lectures. And what I'll be focusing on are the underlying physical mechanisms that produce particle acceleration, particle energization. And these are shocks, wave-particle interactions, reconnection, and turbulence. These are pretty weighty subjects, each worthy of a lecture in its own right, and it will be a real challenge to include all of it in one talk. And so it'll be a bit of a bird's eye view, but I hope in summer schools, that's what you come looking for, and you'll make the most of it. And undoubtedly, I'll omit many important topics in the process. So please forgive me for those omissions at the outset. Let me get into the subject of shocks. And most of you know about shocks, supersonic aircraft. If you have seen one, and most of us have seen a few, when an aircraft goes to the atmosphere at a speed larger than the speed of sound, you know that structure develops ahead of the aircraft as it is speeding up. And eventually, when the aircraft exceeds the speed of sound, you will definitely see the shock form, and a speeding aircraft often emits what is called a sonic boom that you can easily see on many YouTube movies. Those shocks that you see in the atmosphere are very collisional, by which I mean the atmosphere, the molecules in it, are in a very collisional state. On the other hand, yes.
Oops. We have a question from Prabir.
Please,
Sorry.
Prabir, shoot.
Thank you. Could you explain a bit what a standing shock is?
I will come to a picture of that. Would
Okay,
you bear with me just a bit?
Okay, thank you.
Yeah, not at all. It's an appropriate question. I'm just giving certain facts. And the point that I was trying to make here is that there are two types of systems: collisional and very weakly collisional or collisionless. The hallmark of a collisional system is that the mean free path of a collision is much smaller than the system size. That's typical of what happens in the case of an aircraft going through the atmosphere. In astrophysics, though, and heliophysics, most shocks are in collisionless plasmas. And these shocks are known to produce strongly non-thermal particle distributions. By non-thermal, I mean distribution functions which are like your regular Maxwellian. That's a thermal distribution. Now, people who are habituated to the idea of shocks in collisional systems initially founded on that idea, because if you actually get to a system which is truly collisionless, how do you even form shocks in such systems? And this was not taken for granted at all in the heliophysics and astrophysical community. And it turns out historically that until the Earth bow shock was detected by spacecraft, there was debate as to whether or not a shock can actually occur in the solar wind. So it took observations to actually drive us to this situation. And of course, a bow shock, as it implies, is that of, the analogy is that of a speedboat, if you will, in water. When it speeds, as you know, it creates a wake, and ahead of it, such a shock structure forms. Similarly, the Earth as a planet is streaking through the solar wind, and it was plausible that such a shock would form, except for the important issue of how such a shock would come about, given that our common knowledge was based on objects which were immersed in very collisional systems. So let me ask.
Hey, Amitava, can I just interrupt? There's a lively conversation in chat about how to visualize or how do we detect shocks.
And that too I'm coming to.
Okay, great. So what?
I really appreciate all these questions. And you know, preparing for a lecture like this, anytime I hear a question, I feel like I should race ahead to a slide now, but I know that will not keep up the flow. So these are all extremely relevant questions, and I'm coming to that. But now I have a question for you. And what I would like you to do is this. I'm asking this question to the whole class. And I just want to find out where you are about your knowledge of collisional and weakly collisional or collisionless plasmas. So I have a simple question. And what I'd like you to do is to think of the answer to this question. What is the nature of the distribution function in a strongly collisional plasma? And I've given 3 answers, A, B, and C. I want you to take a minute to reflect on it. And then I will ask randomly, one of you, I'll let Dana choose the person, to tell me what the answer is. And we'll see how many people say A's, how many people say B's, and how many people say C's. And depending on the answers, I'll get into a discussion of what the right answer should be. So here you go. The next 30 seconds, please go to the section on participants. And when you're done with your answer, just raise hands, and many people will be raising their hands. I'll request Dana to just choose randomly one person to see what the answer is.
You have 2 so far.
So just to be clear, pick your answer and then raise your hand to let us know that you have an answer in mind. Is that right?
Right. Exactly, Nick. Thank you.
Right. But everybody should pick an answer, even if you're guessing.
Exactly. And we won't be able to call upon everybody, of course.
Amitava, can you explain when you say strongly, like how strongly? Like
By which I mean that the collisional mean free path of the system, that is the path a particle traverses before it collides with another, it's much smaller than the system size.
Okay, I'm going to call on Gwen with her hand up.
Okay, I think it has to be a Maxwellian, but I'm remembering things from plasma physics class where you can have really fun instabilities developing if you have things like two peaks that are separate in your distribution function. So but I don't think that was for a collisional plasma. So I think if it's collisional, you need to have a Maxwellian.
Very good. Any people for B or C? If you are for B or C, then speak up or raise your hand. How will we do this?
Yeah, they can lower your hands if you agree with A, and raise your hands if you disagree. I see no raised hands.
Okay.
Yeah, I have a question.
Oh,
So
okay.
I also, it seems to me that it should be Maxwellian, since it's strongly collisional case. But the thing is that for Maxwellian thing, the volume of the gas molecules itself should be much lesser compared than the entire volume of the gas, I think. Is this the case here?
So let me now get into a discussion of this. So I'm assuming that the votes mean that the vote is overwhelmingly for A, and that is the
Except we do have Milo has just raised his hand. I don't know if he wants to choose a different. Just now, he just raised his hand. I don't know if he's.
Yeah, I'm hesitant between A and B. Because yes, it's Maxwellian when you have a collisional plasma. But then if it is strongly collisional, like let's say you have non-thermal particles in it, then for the higher speeds, you can have any distribution. Sometimes you have power laws and exotic things like that, but then what you ask, it needs to be monotonically decreasing function of speed. So that's why, like, if it is only collisional and is thermalized, I would choose Maxwellian. But if it is strongly collisional, meaning like you have non-thermal particles, I would choose B.
Okay. So, all right. So this is worthy of a discussion. As I just said minutes ago, the answer is A, and that's not obvious for some of the reasons why item B was also mentioned. The reason the answer A is the right ones goes back to a very celebrated theorem called Boltzmann's H theorem in plasma kinetic theory. In my mind, this is probably the most important result in kinetic theory and statistical mechanics of the 20th century. And Boltzmann, who I don't know whether you know, was way ahead of his time in terms of talking about the connection between kinetic theory and thermodynamics. What Boltzmann proved was, and he proved it with complete rigor, that if you have a system in which you have binary collisions, and collisions are dominating in our question by assumption, that the final state must be a Maxwellian distribution. Systems such as B, which have decreasing functions of speeds, will also settle down to a Maxwellian given enough time. So there is no question that at the end of the day, the distribution function must be Maxwellian. Now, in an actual application, what that collisional time is can differ from plasma to plasma, particularly for magnetospheric plasma. Take, for example, whereas 1 particles per centimeter cube, that may be a very, very long time and a lot of things might happen. And therefore, before you get to the Maxwellian. So even in a system with 1 particle per centimeter cube, it might take forever to get to a Maxwellian, and forever is not what you have. And therefore the interesting question then in those plasmas become, is before you get to the Maxwellian, what does it look like? And most of the time when spacecraft observe this, that's what they do. Typically, they're not observing plasmas that have had the time to relax on a collisional time scale. So that's A. Now to the other possibilities that were raised. If you have collisions, say, in a Lorentzian plasma or a power law, Lorentzian is like, falls off as 1 over V squared plus A squared, if you will. That's monotonic, it's decreasing, but it will also eventually become a Maxwellian. Lorentzian plasmas have a little difficulty. They're not physically realizable because their higher moments don't exist, but it's there, that possibility. If you have non-monotonic, like Gwen was mentioning, they will go through instabilities and things like that. But if you wait on a collisional time scale, they too will relax to a Maxwellian. And it all goes back, as I said, to Boltzmann's H theorem. So I'm going to now move on to some examples of shocks. And this is what some of you were asking me. I first wanted to use my first couple of slides to make the distinction between collisional and collisionless plasmas. And now I'm getting to a situation where I'm actually now talking about astrophysical and heliophysical systems, which have the characteristic property that typical collisional mean-free paths are much larger than the system size. And this is Tycho's supernova remnant. It exploded in 1572 and was first studied by Tycho Brahe. And centuries later, the Chandra Space Telescope gave us an X-ray image. What is really incredible about these astrophysical images is that you have these beautiful global images of things happening in the very distant past. And these are, in fact, the only ways in which the astrophysicists know about the plasmas that are there. They do not have satellites or anything like that. It's all by counting photons. So what you're seeing inside there is that there was a supernova blast, and this is what is the remnant. The shock-heated gas, the blast wave is at 3,000 kilometers per second, and interspersed in the green and the brown, if you look at it, you actually see little filamentary structures of blue that indicates very highly energetic relativistic electrons. And this blue envelope that you see is the X-ray emission produced by synchrotron radiation from the shocks. As you know, electrons that accelerate emit radiation, and these relativistic electrons produce this envelope. And there is no doubt from spectroscopy that these are actually produced by tera-electron volt electrons that are produced by this shock. The evidence for TeV ions is actually less direct, but also very strong in a way that I won't get into. So if you look into this image, you have a visual impact, and people were just asking me from class, what would it look like for shock structures? So what I'm going to first do is that I'm going to show, I started with this observation, I showed you an astrophysical one, and now what I want to do is to give you an example of a heliospheric shock. There are many like this in heliophysics. And this is visually very beautiful, the one on the right that you just saw. This is a great global shot. Beautiful though it is, it actually carries very little local information. We know very little about the local properties because we have no probes of these systems. Fortunately, we have images, and a lot of that is also true of our sun, except the Parker Solar Probe will now go very, very close, as close as any satellite has ever been to the sun, and give us will give us now information of a local kind that we haven't had as close to the sun until now. But typically, what you're doing when you are sending out spacecraft is what you see things on the left. And these are picked up by instruments on board this spacecraft. And you're seeing here, as a shock crosses a spacecraft, what the instruments on board typically pick up. And you're looking at magnetic fields, you're looking at densities, and what you see is definite jumps in observational quantities. This, for example, the velocity of protons jump, and knowing your spacecraft velocity, you can actually time looking at this as when you encountered a shock and when that shock actually crossed the spacecraft by looking at spacecraft information and the observations that the instruments are putting out. And what you're seeing as you cross a shock is definite changes in the profiles. This is what I call detailed plasma information of the kind that you can never obtain here. But it would be beautiful if we could have actually seen images as well. This is not equally possible in very tenuous plasmas because the densities are not high enough to actually produce radiation images of the kind that you see here.
Gwen just raised her hand.
Yes, Gwen.
Yeah, I'm just wondering why in this particular example, the like in the shock, the magnetic field magnitude seems really low. When I look at like MAVEN data, the Mars atmosphere mission, and look at them, like the bow shock crossings that are seen at Mars, it's like very noisy in the magnetic field.
Right. And this, I think, depends very much in the local magnetic field topology that exists for this heliospheric shock. So what you're really looking at is a definite dip in the magnetic field line, total magnetic field line magnitude, as opposed to here. You see two levels of it. So it seems, therefore, that this particular shock actually crossed into a region not only where there are density jumps, but also there are magnetic field jumps produced in part by a coincidence of global magnetic field strength as well as the density strength. And these things can happen, as you know, in heliospheric geometry. I hope that addresses your question partially. So it depends very much on what the background magnetic field is doing, where the shock front resides.
Yeah,
Okay.
that makes sense, I think. I'm just used to thinking of field lines piling up, I guess, so.
Exactly. Here it's actually not that.
The opposite, yeah.
The opposite, exactly as you say. And the dependence of the shock properties on the magnetic field line is itself a subject of great interest. You'll see, for example, I'll give you a calculation where I'll actually show you how in certain shock examples, the magnetic field doesn't enter at all, and in some cases it does. I'll comment on that in just a second. This is from a hand-drawn cartoon in Ellison, and also one that Marty Lee did, taken from Scholler. And this is a cartoon, if you will, given the various types of situations where shock can appear in a Helios system. And there are many collisionless shocks. These systems are all collisionless. And there have been spacecraft navigating the entire heliosphere for which we have data. Dana talked about shocks from flares. Jung Kyu yesterday talked about CMEs and the shocks that they can produce. You can have shocks in the vicinity of the Earth, the bow shock, as we talked about, and so on and so forth. And as you go out to the heliosphere and cross over into the interstellar medium, there are also places where there can be solar wind termination shocks. So shocks are everywhere. What is interesting is, and this is why I started with some astrophysical examples, that the underlying physical mechanism for some of these things is the same. And part of my reason for emphasizing the underlying mechanism is because you are focusing right now on physics, do not think that what you're learning is only a heliophysics specific. Gwen just mentioned things on near Mars. Over the entire planet, you have very similar structures pervading. And if you go outside, astrophysical systems have similar physics going on. And so what you learn in one system is transferable to the other. Of course, you'll have to redo everything because the plasma regimes are so vastly different, but the knowledge you pick up in one is transferable to the other. So
we have a question from Krishna.
Go ahead, Krishna. I like all these interruptions. It might mean I will be able to cover less, but I like your engagement very much. So keep shooting. Krishna, go ahead, please.
Yeah, Professor, in the magnetic field variation that you have shown, similar variations are also seen in other plasma boundaries which are not necessarily shocks. Like in the case of Mars and Venus, we have this ionopause where we see such a sharp gradient in the magnetic field. So how do we differentiate the plasma boundary and a shock?
This is a good question. And I am not sure that I will be able to give a completely satisfactory answer. Let me first say that you're absolutely right. In the ionosphere, you have places which are called double layers that you may know about, which are very effective accelerators of particles. And these are essentially fronts over which the electrostatic potential has a significant jump. It therefore produces an electric field that can accelerate particles. So I would not say that all fronts like that are necessarily shock fronts. For the purpose of this talk, the way in which I have defined shocks are those fronts across which certain physical quantities, such as velocity, density, pressure, have a jump discontinuity, which obey what are called the Rankine-Hugoniot type of conditions. These are jump conditions across a front, which do not require special knowledge of what is going on inside of the shock layer, but can be formulated in those terms. And let me use that as the shock definition that you say. And you, as you write, I mean, many of these discontinuous layers can actually have other signatures that would seem shock-like, but are not exactly Rankine-Hugoniot. Okay?
Yes,
Sure. So collisionless plasmas, to summarize, any other question?
Yeah, there's a couple of other questions. So there's
one from Deb.
And there's a couple of questions in chat as well.
Okay.
Questions.
Go ahead, please.
So Laura, Liz, you want to ask your question, and then we'll go to Deb.
Sure. Although it sounds like it might have been answered in the Earth bow shock data that you showed a couple of slides ago. Is that the spacecraft moving through the shock, or is that the shock moving over the spacecraft?
This depends on your reference frame, right? If you are one of the lucky inhabitants, which you are not, because these are unmanned spacecraft, then you would think the shock moved over you. And but if you're in the shock frame, the spacecraft moved over you. If you're standing,
so it's not like yesterday when there was the distinction between a temporal or a spatial variation. That really is reference dependent.
It is reference frame dependent, and if you are observing this standing in the lab, what is really happening is the spacecraft is moving more rapidly. And so that might be your way of describing it. It is frame dependent.
Thank you.
Deb?
Yeah, so I just want to ask a question about the graph you shown in the plot actually, where you can see that B, NE, everything is there. So Rankine-Hugoniot condition says that after the shock, the plasma is compressed. So NE should be high, right, after the shock. But in
It
the
depends on whether it's a compressional shock or a rarefaction shock. Both types of things can happen.
okay, I'm not sure about the rarefaction shock because I think that after the shock,
That's typical what you say.
Sorry.
That is typical what you
Okay.
say.
Okay.
But there are certain examples, and this actually there are astrophysical examples. I won't go into that today, where you would not necessarily always conclude that as you cross the shock, as you come into the shock, that everything is compressing. There are cases where the other things can also happen. Both are quantified though by the compression ratio, which I will define in just a moment. You know, what is very interesting to me is that trying to present this talk, I was wondering how to go about doing it. And your questions are always anticipating some of my slides, which is probably a good thing. I don't know, makes for a lively discussion. But bear with me, and I'm going to get there in just a minute. These are illustrative, qualitative comments, and I'll become quickly quantitative now.
Okay, sir. Thank you.
Any other questions, my friends? Okay. Okay. Any more? No, okay. So collisionless plasmas, just to recoup, the density rho, as I said, is low enough that particle-particle collisions are rare. And this is typical in solar wind. The particle-particle mean free path is on the order of the sun-Earth distance, okay? There are, however, turbulent magnetic fields in all these systems. So even though there are no real collisions, charged particles can scatter off magnetic field fluctuations because, and I'll just show you a picture to illustrate that. They can pitch angle scatter in turbulence and have effective mean free path, which we are calling LB, to designate that it is brought about due to magnetic field fluctuations in the background, which actually give you a scale length which is smaller than the system size. And such systems we see in the solar wind and interstellar medium, in planetary bow shocks, in supernova remnant shocks. And here is an example of NGC 2736, a pencil nebula. You see this very thin structure. This is not a collisional structure. If you look at what the collisional mean free path in these systems are, these are way larger than the range of this image, the scale length of this image itself. So how does this come about? Well, qualitatively, suppose if you have uniform magnetic fields, I hope somebody is keeping track of the time and will tell me when the break should come.
I am.
Okay, thank you, Dana.
Keep going.
If you have, can you tell me how much time I've taken so far?
Yeah, it's 8:15 and you started more or less a quarter of, so you've only taken half an hour.
Okay, great. Thank you, Dana. So you have charged particles now, uniform magnetic fields. You all know what you expect, the spiral things, right? These actually are well known to you. Gyrotron motion, there's no scattering here, okay? Now imagine the background magnetic field is not very strong and it is perturbed by fluctuations, electromagnetic fluctuations of the kind that often accompany instabilities in plasmas, of the kind that you yourself mentioned to me earlier. Like what would happen if you had non-monotonic distribution functions or things called loss cones and stuff like that. They can produce electromagnetic instabilities and turbulence. So in addition to a background uniform B, you have a delta B. And often delta B is of the same size as B. So it perturbs the background field significantly. And you can well imagine a charged particle which is going through gyrations in the local magnetic field. But because of the spatial changes, essentially ends up going on a path that brings it back. And this has the look of as if the particle suffered a collision. Like a wall it ran into or something. It's much more gradual than that. And in this sort of a scenario, the reflection process is nearly elastic, as if the particle scattered off a reflecting wall, but is now going the opposite direction. So even though you did not have real collisions with other particles, the magnetic field, turbulent as it is, provides a way to scatter particles in a way that real life collisions do. So this is therefore an underlying mechanism, the background turbulence of scattering in a collisionless system. And therefore, in the study of astrophysical and solar plasmas in collisionless systems, you will find that shock and turbulence goes hand in hand. When people try to simulate these things using particle and cell codes, fully kinetic codes, they come into situations where you will see that there is an overall shock structure developing. But in the background, in the ambient medium, there's a lot of turbulence going on. And the study of what kind of turbulence can enable scattering of this kind and can sustain a shock front, despite the absence of collisions, it continues to be a very important area of study. This is why people write hybrid codes or particle and cell codes, and why this is such a rich area of work with many unsettled questions. I finally come now to giving you just a little bit of mathematics of what we call the Rankine-Hugoniot condition and what a standing shock looks like. Well, this is now in a reference frame in which the shock is at rest. So imagine you are moving with the shock. The shock is therefore stationary. With respect to you, you have flows hitting you from the left and going to the right. Very simplified one-dimensional shock picture that I'm finally showing you. A vertical line distinguished by the fact that the quantities of plasmas across this go through a jump, as indicated by the velocities u1 and u2. Imagine that you are in steady state. So this is one-dimensional situation, no curvature, nothing. So the first equation is one of continuity. Del del x of rho u equals 0. That's mass continuity. Notice the second equation, you have no magnetic field. So we're looking at a situation where magnetic fields aren't playing a role. It's purely hydrodynamic shock, if you will, fluid. But that fluid is a plasma, but we can learn a lot from these kinds of solutions. So you're looking at a kinetic energy plus thermal energy, steady state again, no del del t term, momentum plus pressure. Second is of energy. You have three equations. And so if you integrate across this jump, and let me call the quantities in region 1 by 1, quantities in region 2 by 2, by just integrating across the discontinuity, you can show, and you can show this with a pen and paper without too much work, and I won't make you go through this in this lecture. Let me just give you the answers. Rho 2 over, and this is obtained by purely matching quantities on the left-hand side with quantities on the right-hand side as dictated by this conservation laws. You get these equations. Rho 2 by rho 1 equals u1 over u2 was gamma plus 1 by m1 squared by gamma minus 1 m1 squared plus 2. Gamma is 5/3 for three-dimensional problems. For one-dimensional problems is something else. M1 is the upstream fluid Mach number. And this is in fact your temperature equation, T2 over T1. So this is what comes out of these three equations. And this is what I call the Rankine-Hugoniot conditions, jump discontinuity across this shock. If you go to the strong shock limit, where the Mach number is much greater than 1, these equations simplify. They become this. Rho 2 over rho 1 equals u1 over u2, this. P2 over P1 is this. T2 over T1 is this. T2 is simply given on the right-hand side. You have simply rewritten what T1 is in terms of the energy and you get this. So one can see that shocks behave as very efficient heating machines in that a large fraction of the incoming ram pressure is converted to internal energy of the gas behind the shock front. This is in the strong shock limit, you actually see this emerge from this simple equation. Now, I have a simple question for you that I would like you to go through this exercise again. The compression ratio is the ratio of rho 2 over rho 1, or similarly T2 over T1. What is the compression ratio in this problem in the infinite Mach number limit? And imagine you're doing this problem in a system where the specific heat is given to you to be 5/3. So I show you this result and I give you 3 answers. A, infinite, B is 0, and C is 4. 3 seconds, not 3 seconds, 30 seconds to answer my question. Let me go back to the result. You're looking at a very strong Mach number limit.
Is it 4?
Yeah, it's 4.
Okay.
I was going to call on someone, but yep.
I think it's so obvious, right? I just wanted to check that you're still up with me. So what is interesting about this is that in this very simple limit, it actually, your answer is right. There is a universal number. In the strong Mach number limit, the compression ratio is always 4. So that's beautiful. Unfortunately, it's not a universal result. There's no magnetic field, nothing in it. And I'm going to complicate the problem for you by actually telling you later on that magnetic fields do matter. It just is that we were looking at what you would call a very simple shock front in which there was no obliquity of the shock at all. It fell directly on the boundary and moves on. So parallel shock and perpendicular shock, where the shock normal is actually parallel to the boundary here. And I want to tell you a little bit of history about this. It turns out that most of our knowledge really regarding shocks goes back to 2 classic papers by Fermi. One was written in 1949 and the other in 1954. And remember, these were days predating most of what we know to be true of the solar wind today. And Fermi was stimulated by Hannes Alfvén's work and the work of Hoffman and Teller. Edward Teller, as you know, who's largely regarded as the father of the hydrogen bomb, was in fact Fermi's colleague in the celebrated physics department of the University of Chicago. But it's worth reading this paragraph because of some of the words that Fermi uses. A particle that finds itself between 2 such regions, and what he was looking at was regions where they have shock fronts, will be trapped in the stretch of line of force comprised between them. Imagine there's a magnetic field line that's lying there. When this happens, the energy of the particle will change with time at a rate much faster than usual. It would decrease or increase according to whether the jaws of the trap, he says. So he had in mind 2 mirrors, if you will, which are reflecting particles going back and forth, and these mirrors, say, are gradually approaching each other. There is a very nice law of physics called the adiabatic invariant, which simply says that the parallel velocity multiplied by the length between the 2 mirrors is a constant. So you can imagine if the length drops, the parallel velocity will rise. And Fermi had in mind that something like this would be a good way to accelerate particles. And he says, recently, D. Hoffman and Teller have discussed the features of magnetohydrodynamic shocks. They show in particular, and this was theoretical treatment, that at a shock front, sudden variations in direction and intensity of the field are likely to occur. One is tempted to identify the boundaries of many clouds of the galactic diffuse matter with shock fronts. If this is correct, as we have a source of magnetic discontinuities. Fermi postulated that shocks could trap particles. This is first order Fermi acceleration in the sense that the amount of energization you get is actually dependent on the change in momentum, and it's called first order because you can actually show that it really depends on P, and you get this famous universal power law. And here Fermi did not derive it, but what came to be known as diffusive shock acceleration, or DSA in shock language, is nothing but the so-called first order Fermi acceleration mechanism. Here are some review papers, classic ones at that. Ellison, as I said, did a very important educational purpose for all of us, but classic papers by Axford, Blandford, and Eichler in the astrophysics community. Fermi's 1949 paper, as it turns out, is actually a second order Fermi acceleration model. The application to shocks is more the 1954 paper, which I just showed you. And that actually predicts a universal power law for relativistic particles in momentum proportional to 1 over P4. So it turns out that you get this universal distribution function. This was not derived by Fermi, but by subsequent authors. But Fermi was the person who first identified this mechanism. Are you guys with me?
So yeah, there are two questions, and maybe we should take those. And is this a good time for a break?
Sure.
I mean, after the questions in your talk.
Sure.
Okay. Giuseppe's had his hand up. I'm not sure if that was in a response to the compression ratio, or he had a separate question.
You're talking. Yes.
Yes.
Yes, I was about to, it was about the compression ratio. I know that it was for, okay.
Oh, okay. But Stefan has raised his hand a little bit later, so he might have a question. No, it's gone.
No, it was still raised from before.
Oh, okay, it's gone down as well.
So Dana,
okay.
do I have your indulgence? Maybe to just maybe do a little.
Oh, right. Sorry about this. Okay, let's finish. Yeah, whenever you can break, whenever it makes sense.
So I'm lagging behind a little. Let me just. So I wrote down a result, right? F goes like 1 over P4. Now I'm going to try to derive that result for you from first principles, from something what has come to be known as the Parker equation. But before I tell you what the Parker equation is, I'm going to ask you a question. When you look at that equation, what is it? It's also, I hope, a fairly easy question. Do you recognize it? It's a wave equation, or a diffusion equation, or a frictional drag equation? Put your hand up when you have an answer.
Well, it's not random, but I'll defer to Giuseppe because he had his hand raised from before and didn't get to answer the last one. So Giuseppe, are you?
Hey, yes.
Yes. What's the answer here?
About this question?
Yes. Or is that a mistake? Is your hand up for something else?
But what kind of we are talking of what kind of an equation is this?
Right, and I've written down the possibilities. It's a wave equation, a diffusion equation, or a frictional drag equation.
Equation, all right, yes. This is a diffusion equation.
Okay. Any other opinions on this?
Lots of hands are up, and many of them are being lowered.
Wave?
Oh, someone is saying wave, okay.
Okay.
Few people have said wave.
Uh-huh. And anyone for frictional drag? Okay. So let me quickly address, since there is a division of opinion, we haven't counted. This is a diffusion equation. If it were a wave equation, it would have two derivatives on the left, and of course, assuming D is positive. And let me give you, this is not an uncommon mistake, so don't be embarrassed if you thought this was a wave equation. If there were a wave equation, it would have one really important property, which is that a wave traveling backward in time or forward in time wouldn't make a difference. It would be the same wave, and the equation would not be irreversible. So you would usually have an extra derivative, del square f del t squared. That equation is invariant to the transformation of t going to minus t. Notice though that this equation is not. This actually is a time irreversible equation in that if you change t to minus t, the equation changes. That's the indication that it's an irreversible process. It's called a diffusion equation. Heat conduction in a rod, or if you go from a system where you have a density gradient, F could be n, del n del t equals d del square n del x square. That's the diffusion equation. And frictional drag usually has something like a force term, m d2x dt square equals minus nu dx dt. And that term, that equation is certainly not even farther away from this equation. So it's a diffusion equation. When you return from the break, Dana, could we keep that a slightly shorter break? Because I'm
yes. Let's make a 5-minute break.
5-minute break, and then what I'll tell you about is the Parker equation. Thank you very much.
All right, let's be back in 5 minutes. So 8:36 in the Mountain Time.
Very nice, Amitava.
Well, thank you.
You know, for the first time, I'm able to actually spend time listening as opposed to being in the back of the room and see.
That's an
Except
interesting
today,
point.
I am triple booked. So, but no, it's very, I'm really impressed at the level of kind of fundamental questions the students are going at.
Yeah.
And this is exactly what we need to pick up, emphasize, not only in research areas, because research just goes on in its traditional ways, and we don't come up with breakthroughs because we just kind of are afraid of thinking like the kids do.
Yeah, the students are not afraid.
No,
this is the thing.
no.
This is why they are the agents of change.
Yes, and we need to kind of try to make that, you know, push that.
Yep.
Our system, the bureaucratic system.
For those of us who are privileged to be faculty members and who have the privilege of having great students, I don't think I'm saying anything original by saying that I've had that privilege a lot of my life, not all. And without the contribution of these students who taught me most of my life after I spent an initial time teaching them, my career would be nothing without them. So you rely on these people because they're less prejudiced than we are, and therefore able to make real changes. I'm continuously struck by that.
Yeah, I think this is you know, I'm kind of thinking, how do you reinvigorate the research process that we support? Because when people write proposals, it's just kind of falls into a format. Yeah. Yet we are looking for breakthroughs. I mean, breakthroughs happen when you ask this question, then you allow them to go pursue it. Go solve some equations.
Yeah.
Yeah, I have missed out largely this particular world, but you know, at least I'm fortunate that I have been able to keep myself engaged at some level to see.
But look what you've done, created this summer school and allowed other people to have this opportunity, and that's great.
And then that's work, but you know, this is it cannot be a closed system. It has to continuously evolve.
Right.
We can use any of your PDEs or shock system to kind of draw analogies that it can't be stagnant. We have to be moving. And it kind of, you know, just kind of having these opportunity to virtually engage, my mind is interacting differently and kind of thinking of the next set of things we must do.
Mm-hmm.
I mean, this is a place where we should kind of incubate ideas, pass it on, not from just, you know, traditional community as we do, right? There should be this mixing in.
Mm-hmm.
Just thinking, thought I'll share.
Yeah. Dana, you'll signal when I should begin.
It is. I was just about to jump in here. It is time to start back up again.
Thank you, Dana.
Yeah, thank you.
You can see my screen, right?
I can. It's again on presenter mode. So
yeah. I shall fix that.
Right. Oops. That goes all the way back to
my mistake.
Oops.
Okay.
Okay. You're on.
Now, I introduced to you the diffusion equation with a purpose, because I'm about to introduce to you an equation that goes back to Eugene Parker, who, as you know, is responsible for many of the important discoveries in creating the heliophysics discipline as we know it today. This equation, the one that is written on top, is what is called the Parker equation. It's a very well-known equation and a very confusing equation. And that's why Marty Lee, when he gave his lectures in this summer school, pointed out that whereas it is called a convection diffusion equation, among people who know what technically things mean, of course, the first term on the right-hand side is exactly the term that you just encountered when you decided that these two equations define a diffusion equation in response to my last question. But there is a convection term, and there is a compression term, and there is an injection term. These are new pieces of physics. The derivation of this equation from either kinetic theory or fluid equations is a subject, believe it or not, of still debate. Parker derived it himself from the fluid approach, and I can't go into that too much, but let me just give you this equation, and I will give you a bit of a discussion on how you get equations of these types, which are often referred to as quasi-linear diffusion equations, which are immensely useful in analyzing particle acceleration problem. In the community, what Parker's equation covered and did not caused a great deal of confusion. And there were people who believe in it and people who defected from the ranks. This debate, by the way, continues. So sometimes this equation is referred to as the confusion defection equation of Parker. But nonetheless, let me assure you that this equation has now been looked at by a number of people, and they've been able to derive it under conditions, under assumptions that were not sufficiently well and clearly laid out in Parker's paper. Parker is an intuitive genius of sorts, and so he often arrives at answers that are correct without necessarily almost correct sometimes too, that do not necessarily get written down in his paper in the form of strict approximations. And this is where some confusion sometimes lies. People do not know what the realm of validity of the equations are. But let me assure you that it has been looked at, and the realm of validity have generally been understood now. But let me use an application of this equation. And I promised you that I'll give you a quick derivation of Parker's, Fermi's universal distribution function law, that Fp in the case of that shock that you saw scales like 1 over P4, and it comes out of the Parker equation. So here is up and here is down. Here is the shock front, U1 and U2. Assume steady state, put this term left-hand side to 0, and integrate across this jump discontinuity. So if you have del x, you integrate across, you get d del f del x on the second side with jumps to 1. This is the convection term. U is the fluid velocity. This has this feature. Oh, I'm sorry, I misspoke. UF del x, when you go through, F has no discontinuity, so this term drops out. This term actually gives you a discontinuity. And this is the value itself, the matching value at the shock front. If you go from infinity to 0 minus, that is, you come up to here, the same equation gives you this quantity. And requiring that the system be homogeneous downstream, another approximation, you can just apply this equation to the right-hand side. And since there are no inhomogeneities, you're going to set these terms to 0, whichever has del x in it, and you end up getting this result. If you integrate this simple equation, you actually can derive a power law, F0P, as a solution to those equations that I wrote down before, where n is the number of particles you injected, p is the injected velocity, and this actually brings out to you injection being what is happening on the left side. This actually highlights an important challenge for all shock problems. It's called the injection problem. You are taking particles here which are at some velocity, and you are changing their velocity, accelerating them. But how many you inject and at what velocities does determine what you get. Sometimes in solar wind or in heliophysics or in astrophysical situations, it isn't clear where the injection is coming from. And therefore, people who run particle in simulation codes and stuff often make assumptions, because they can only do finite boxes, that such an injection population is really available. Nonetheless, people are very mindful that this is a parameter that they actually control. And therefore, a complete solution to a shock problem would require not just knowing the power law, but also solving the injection problem. But be that as it may, in the limit in which you do the strong shock, which you just did, R tending to 4, you know what U1 over U2 is, so you can write out what this is. And you notice that if you take the number density of particles that lies between P and P plus dP, then you get 4 pi P squared F of P. Now, if you take the compression ratio of 4 and you plug it in here, you get that F should scale like P to the power minus 4, exactly as we said. And then the number density, because it's multiplied by an extra factor of P squared, scales like P minus 2. So one infers from this exact solution that the spectrum of accelerated particles is a power law extending to infinite momenta. The slope depends uniquely on the compression factor and is independent of the diffusion properties. Notice that in the very high Mach number limit, D has fallen out of the problem. No magnetic fields are there anyway. Injection is treated as a phi parameter which determines the normalization. So this is a highly simplified but rigorous set of results that allows you to understand something about the shock problem, which is why I chose to do it. But in so doing, I actually simplified what is a real life situation significantly. Because in real life situations, this angle, theta B0, which was 90 degrees for us, is not necessarily so. Usually, first of all, if you have a planar shock, you will have oblique magnetic fields, which might change direction across the planar shock. And then if you write down the Rankine-Hugoniot conditions under these cases, you will find that it's not possible to drop out the magnetic field. In other words, you could have asked me the question, you use only hydrodynamic equations. When do those equations become exact? Well, they become exact when you are actually dealing with the problem, which is non-oblique. And what you get is then 6 equations instead of 3. And you can still have, in addition, this planar shock approximation and steady state that you build in, but the answer becomes more complicated. I won't get into the complicated problem except to tell you that the pictures that you saw me draw in that cartoon are full of oblique shock situations. And in order to deal with them rigorously, you really need to deal with numerical solutions often. Notice the Rankine-Hugoniot conditions, one thing that I should emphasize, really has got to do with jump conditions, which are far away from the shock front as you move out. And I'm not resolving the physics of what is going on in this boundary itself. This shock discontinuity boundary is regarded as an infinitesimally thin boundary across which certain conditions jump. But in point of fact, all these shocks have finite widths. And so the infinite or the sharp jump that you see is an idealization because there is across this thin boundary, because there is usually a finite width. What controls the width is really the dissipation mechanism. And in collisionless shocks, that's usually turbulence, particle inertia, things such as that, which have nothing to do with collisions, but determine what the shock width is. Okay? Now, I'm now moving into a slightly different subject, which is wave-particle interactions, which is the second subject I listed. And what I'd like to do is to tell you how you can get diffusion type of equations in the treatment of such cases, beginning from fundamental principles. And now the fundamental principle that I'm writing down is what is called the Vlasov equation. Dr. Schrijver has in his book laid out this equation as the beginning point of many of his discussion. This is the distribution function F in the presence of electric and magnetic fields. V is the velocity. So F is a function, distribution function that depends on displacement, R, velocity, V, time, T. E is the electric field that depends only on R and T. B depends only on R and T. This is what is called the Vlasov equation. On the right-hand side, you have 0. I have a question for you. What can you say about steady state solutions to the Vlasov equations? Now I'm setting del T equal to 0. And I'm sure all of you have heard about the Vlasov equation, which applies now to collisionless plasmas. So I'm getting to a question similar to what I asked you for collisional plasmas. And I've given you 3 answers. It must be a Maxwellian, it can be any function, or it must be a function of constants of the motion of a single particle, as for example, energy.
C probably.
Okay. One answer has been offered, C.
See?
So you want people to raise their hands again when they've chosen
Yes,
it?
please.
Yeah, yeah.
Please.
I'm waiting to see hand raise.
The protocol remains the same. Sorry, I should have probably repeated it.
Nope, hands are going up, so. Oh, Deb has a hand up.
Are the answers not, are the hands not going up because everybody agrees with C? Or?
Yeah, so for this case, I think it may be Maxwellian because There's also like steady state solution, equilibrium condition. I'm not sure though, because of the equilibrium point of view, I can say, because like it is similar to Boltzmann's equation, except the field, magnetic field. And for Boltzmann's equation, the equilibrium solution is the Maxwellian form. So that's why I'm guessing. I'm not sure though.
Okay.
I think it must be a Maxwellian too, because
Okay.
we assume always in course of plasmas that we have a Maxwellian distribution for collisionless plasma, but I don't remember why.
Okay. So let me remind you a little bit. One really important difference from Boltzmann's equation, and you're right, Boltzmann wasn't dealing with plasma physics, he was dealing with neutral gases, and so he didn't have magnetic fields or electric fields for that matter. But he did have something really important on the right-hand side. It was the Boltzmann collision operator. Remember? Boltzmann said that in the presence of collisions, you get a Maxwellian.
Yes, yeah. So one-to-one collisions are important there, right?
Exactly. So now what you're seeing in Vlasov, other than the complicating feature which you did mention, I agree with you that this equation has electric and magnetic fields. But in my mind, the most profound difference between Vlasov equation and Boltzmann equation is Vlasov equation has no collision operator. And therefore, in the absence of collisions, Boltzmann's H theorem does not apply. And therefore, the unique final state of the system need not be a Maxwellian. But if you put del delta equal to 0 and say, what are the solutions of this equation which are exact? I don't know how many of you know about the method of characteristics, which I will mention in just a moment. It actually tells you that this equation can be completely solved by particles, by knowing what the single particle equations are. And the single particle equations are dr over dt equals v, dv dt is equal to this. So those are just two single particle equations. And if they have exact constants of the motion, like energy, momentum, angular momentum, and so on and so forth, all of those, the function can be functions of. The distribution function can be a function of constant of the motion of a single particle. It could be energy, momentum, angular momentum. Now, obviously, the Maxwellian depends only on energy. So it is a particular possible solutions, but this class C is more general than the class A. And that's why in collisionless systems, you actually have the possibility of seeing distribution functions that are very different from Maxwellian. Now, I think this is really an important lesson for you to learn, right? Because we are saying that heliophysical systems or astrophysical systems often have distribution functions that are not Maxwellian. If Boltzmann were completely right and applicable, why are we observing these distribution functions? We should all be measuring Maxwellians. Well, the answer is that the collisions are so weak that the collisional equilibration time for these systems to go to a Maxwellian is far longer than any time scale of measurements, which is why space plasmas are so rich in finding deviations from Maxwellian. And if they are steady state, and if there are directions of symmetry in the system, like in a particular direction, nothing changes, you will find the distribution function is a function of the energy and the momentum that is preserved because there's a particular symmetry direction in the problem. So the answer is C. So now what I want to do is to give you a little bit of background, and I'm going to go, I'm going to not bore you with algebra, but I'll tell you what goes into the assumptions of deriving a diffusion type equation from this. And the technique is called quasi-linear theory. There are pioneering papers that do this that are listed there. You write the f as a distribution function, f0 plus a perturbation. This is for separating the background from things like turbulence. Similarly, you have a uniform magnetic field perturbation, and assume that there are no background electric fields. The assumption here is that because electrons and ions in a plasma, in a fully ionized plasma, if there is a charge separation that creates an electric field, the electrons move very rapidly to get rid of that electric field so as to make the background as field-free as possible. Now, this is, of course, there are exceptions to this rule, double layers in ionospheres where you don't have this happen very much because of the strong collisional processes that get in the way of electrons streaming too freely. But we won't get into that. We're looking at collisionless systems here. So B0 is the uniform background magnetic field. F0 is the background. And if you suppress the time dependence here, it will be a background equilibrium distribution function. The reason why sometimes people pick the time is because there is an equilibrium, but that also often evolves very, very slowly compared with the time scale of evolution of the fluctuation, which happens much more rapidly. So even though T is mentioned in both, this is much more rapidly varying than the background. And if you in fact take this as a very slowly varying del del T, then you can solve this equation. And it turns out, that an equilibrium solution that can be made up is that of V perp and V parallel. This is what is called the anisotropic distribution function, not the same V. It could have a T perp and a T parallel. It could be Maxwellian in each direction, but not a total Maxwellian, which depends only on V. So if you use a cylindrical, that's just an example. So if you use cylindrical coordinates in velocity space, but the cylindrical axis is aligned with B0, soon we will set B0 to be Z and V parallel will become VZ. And here we are making the point that F0 varies in time over time scales much longer than the wave periods or the fluctuation periods. And here, the time that is there is describing time variations over time in F1 comparable to the wave periods, and F0 doesn't vary on this fast time scale. So think of this as essentially fixed in space. In point of fact, is varying slowly. But on the rapid scale of the fluctuations on top of it, it isn't doing much. Well, then you can separate out the problem into two parts, an equilibrium part, which you just solved, and a fluctuating part, okay? Notice this. This is like the linearized Vlasov equation where you're plugged in. F0, assume there's no time dependence, drops out. The first term gives you del F1 del T. The next one is V dot grad F0, that's included here. These add up to 0 separately for equilibrium. For the perturbed quantities, you have this. And on the right-hand side, you have a driving term arising from the velocity dependence of the zeroth order distribution function. Okay? So this whole operator, del del T plus V dot grad plus Q over MC V cross B0 is often written simply as a DDT operator. And you solve for X and D and VT. These are the so-called characteristics of the equation, which allows you to write this as dx over dt as V, this one as dV dt. So this becomes dF1 dt, and you solve for xt and vt. So the strategy is simple. Solve for the F1 equation, and then plug it in the equation for F0. So let's do a simple case. Uniform magnetic field is going along, dx dt equals V, dV dt is equal to this. Imagine B is along Z, so Vz is constant. You know this very, very well. And the perpendicular velocity is also a constant. So you have helical motion at the cyclotron frequency of omega, QB0 by MC, with gyro radius given by rho V per over omega. This is single particle orbit, exact orbits of the system. If the field line is curved, there are other kinds of drifts. In my magnetospheric physics lecture, which will come on Monday, I'll get into those kinds of orbit discussions so that you'll have a bit of background as you go into Professor Nip's lecture, which will come to you later. I promise you I'll cover those drifts then so that you'll be prepared for it. But here we're going to do the simplest kind of a drift. So once you do that and you solve the equation for F1, after a lot of algebra, you get this equation. I know it looks very, very daunting, but I wanted you to make sure that you understood how such an equation is derived. And notice what we have done now is this F is now really F0. This is the equation for the background distribution F0. So I kept telling you that the background distribution function evolves in time slowly, while the wave fluctuations on a much more rapid time scale. What we are doing here now is to derive an equation for the time evolution of the background distribution function, F0, given that you have a lot of fluctuations that are rapid, F1, B1, E1, and we haven't prescribed what the instability source is. We just developed a general theory in the presence of a uniform magnetic field that tells us about the time evolution of del F0 del T as a result of the fluctuation. So think of this as F0. Now look at this equation. The G operator is del del V in it. It is separated into a del del V perp and a del del V parallel. This is just a general form of the equations. But if you look at this derivative and you look at this derivative, there are two velocity derivatives here. So on the left-hand side, you have a single time derivative. On the right-hand side, you have two velocity derivative because there is a del del V here and there is a del del V there. That's a diffusion equation in velocity space, very reminiscent of the diffusion kind of a thing that you had in the Parker equation, or in more generally as shown here for this quasi-linear equation. Now, this is multiplied a very interesting function, which is called the delta function, the Dirac delta function, which has the property that if this term is 0 inside, then you have 1, otherwise it just vanishes everywhere else. In other words, the resonance condition, which we are now going to deal with, has a very important piece of physics to play, without which a lot of this doesn't make sense. Notice that on the right-hand side, you have an amplitude dependence of the wave. These are Bessel functions. Don't worry about that. Anytime you have magnetic fields, these Bessel functions come in as discussed in the book by Sticks. Those are just technical details. And I don't want you to lose the forest for the trees. What I'm after here is the following. We said there were no collisions, okay, in the system. Okay, then we said from a very pictorial point of view, that fluctuations play the role of collisions, okay? But collisions make particles diffuse, okay? Now we have fluctuations playing the role of effective scatterers. So we should have then an equation in velocity space, which will allow us to diffuse particles without any actual physical collisions, but with waves playing the role of collisions. Well, that's exactly what you have in the physics of this equation. Del F del T on the left-hand side, a diffusion coefficient, which depends on the amplitude square of the wave, and two derivatives in velocity working on F. And what the quasi-linear theory has done is to given you a time evolution equation for the background distribution function F as a result of the fluctuations. Are you guys with me?
Yep.
Good. If you miss the details of Bessel functions, don't agonize over it. You can always go and read Sticks or Kennel and Engelman's paper. That's detail. The physics is what we are after here. So what does this wave particle resonance condition mean? And I want to give you the physics of it. Consider a electric field fluctuation of the plane wave form. Okay, let X be, so the streaming and a magnetic field. So you're looking at parallel motion along the magnetic field, sorry. The primed frame moves with the particle guiding center. What is the guiding center? The guiding center is the center. It's a fictitious thing. A particle is going around in Lama radius. The center is tracking the magnetic field line while the particle itself isn't. And that's what is called a guiding center orbit. You will find that when I talk about drifts tomorrow, the guiding center orbit that Dr. Schrijver talks about in his book becomes very important, but that's for tomorrow. In the primed frame moves with the particle guiding center. So now consider delta E, which is of this form, and I write X as X prime plus V parallel BT, and you get this Doppler shifted bit in the prime frame. So then omega minus K parallel V parallel is really the Doppler shifted frequency in the guiding center frame. When does the wave particle resonance occurs? When omega minus K parallel for the wave resonates with one of the ion cyclotron frequencies, which is EB over MC. N is it could be the first harmonic, the second harmonic. All these are cyclotron wave resonances. So what quasi-linear theory does then in this form allows you to understand how to track, for example, the effects of ion cyclotron resonances in these sort of problems. And the whole problem of solar coronal heating, which is observation of, say, Esser et al., where you see oxygen and hydrogen heated to very high temperatures, you will see often that ion cyclotron frequencies are, these are, by the way, minority ions. These are protons, and you see them heated to these high temperatures. Ion cyclotron heating is an ideal candidate for heating mechanisms, and quasi-linear theory is frequently cited as a mechanism for producing these sorts of anisotropies as you get closer and closer to the sun. You know, solar probe, Parker Solar Probe, we'll be looking at some of these, and I should explain to you, because I can't go into details, but ion cyclotron is by no means the only mechanism that is touted as a possible mechanism for ion heating. In fact, there is turbulence, there's ion cyclotron resonance, there is magnetic moment destruction by turbulence. All these mechanisms are competing for attention of observers on which are some of the better mechanisms. So it's an area of work that is going on. What is common is that T-perp is much greater than T-parallel, and theories for this will be ones that Parker Solar Probe might be able to discriminate between for the first time in the history of solar physics. So it's a very, very exciting mission, stay clued.
So before you move on, Satabwa has a question.
Please, Jenna, how much time do I have?
Yeah, thank you.
If you could wrap up and find a place in about 15 minutes or so.
We'll try. Thank you for
telling us
telling.
a break before our yeah.
Okay.
Yes.
Go ahead.
I just have one doubt. So it's not really clear to me what is exactly mean. I mean, what is the physical meaning of wave particle resonance?
Okay. So that's very, a very pertinent question. So omega is the property of the wave. That's the wave part of this statement, wave particle resonance. The cyclotron frequency is a particle property. Forget, for example, for the moment, think that you have no Doppler shift at all, okay? Just consider a special case. What will happen in that case is that a property of the wave, omega, which is the sinusoidal frequency of this, matches a particle property. That is what I mean, omega equals n omega then is a wave particle resonance, because a characteristic frequency of the particle matches the wave. And when that happens, you have the particle, electric fields can accelerate particles, as you know. It's a little bit like the pendulum problem, right?
Okay.
You can in fact force it, and you can drive the particle at resonance with increasing amplitude if your force resonance condition is met. The K-parallel Doppler shift is coming about as a correction. It's a combination of the wave and the particle in a way, and that might be the confusing part. But it essentially is saying if you move in the wave, define a new omega prime, because you know you're not going to see the wave but a Doppler shifted frequency. But that's what I really mean. Is that clear now?
Okay, so I mean, what attributes of the particle should I expect to get attenuated due to this resonance?
To be attenuated. What you actually expect is effective energy transfer from the wave to the particles if you have heating. So the fluctuations would lose energy and the particles would gain. That's when you heat. If you've heard things like Landau damping, where you have a monotonic distribution function and a wave damps, what happens there is the wave is giving up energy to the particle. And that doesn't have to be a cyclotron frequency. That also happens to be omega equals kV, right? Remember the lambda resonance occurs? Now the only difference is that omega minus kV is the Doppler shifted frequency that is resonating with the ion cyclotron frequency. And this has the potential to heat. Okay?
Yeah. Thank you. Thank you.
Okay. Do all of you know about magnetic reconnection? I have 15 minutes, and I would prefer to actually assume that you know magnetic reconnection. Is that a reasonable statement?
Can we do a thumbs up and thumbs down on that, Amitava?
Okay, thank you for telling me. Let me therefore quickly define magnetic reconnection. And what I'm going to do is not ask you too many questions and take questions at the end. Okay. This is my favorite subject, something I know a little bit about. Ideal MHD Ohm's law, all of you know. E plus V cross B equals 0 on the right-hand side. And this has a very important consequence. It is that B lines are frozen in the plasma, by which we mean that if you take a contour in a plasma and magnetic field lines are threading it at some time t, at later times, the flux in this surface is always going to be conserved as long as this equation is valid. There's another way to state the same thing, that if you take plasma particles that you mark on, say, a magnetic field line, and then you follow that field line, follow the plasma particles, and you will find that if they lie on a field line initially, they'll do so for all times. This property is what is called the frozen in flux condition, or Alfvén's theorem, first derived by Hannes Alfvén, who, as you know, got a Nobel Prize in plasma physics, the only Nobel Prize winner in plasma physics ever. And some people make the cruel joke, that's because he was a Swede. We like to think because the Nobel committees don't like plasma physics. I don't know where the truth lies. More people should be getting Nobel Prizes in plasma physics. Anyway, that's an insider's joke. What happens is that if you have ideal plasmas and you have something on the right-hand side, like R, which has the property that curl of R dotted with B is non-zero, then Alfvén's theorem goes out of the window. And you have field lines that break and reconnect. Example, R could be eta J. The curl of eta J is non-zero. Field lines can break and reconnect. But it's not the only thing that can break or reconnect field lines. Particularly in collisionless plasmas, you have things like electron inertia, pressure tensor, which are well-known properties of a generalized Ohm's law that break field lines. Well, what do breaking field lines look like? If you have two field lines that come together, they can pinch and break off and go off. And due to this process, they can liberate enormous amount of magnetic energy that can show up in kinetic energy. So it's not inappropriate that magnetic reconnection is also a major agent of transfer of energy from magnetic to kinetic, or particle energization, as you've heard people talk about. I will not show this movie. You have seen beautiful movies like this throughout the lecture. Flares suddenly take off. In the Earth's magnetosphere, you have a very important role for magnetic reconnection playing a role in magnetospheres as well. I will dwell on this. Also in the next lecture, given the shortage of time, I'm going to rely on the knowledge that you know there are things like storms and substorms where enormous particle energization occur because of the process of magnetic reconnection. And what I am out here is to discuss with you what some of these mechanisms are. The most important model in magnetic reconnection theory that's well known to you, to many of you, is the so-called Sweet-Parker model for magnetic reconnection. In fact, I think Professor Chu addressed this in her lecture yesterday, if I recall correctly. Basically, what you have are systems of oppositely pointing field lines. And suppose if you have a slow inflow coming in, You form an extended current sheet, and imagine it's a steady state process, inflow leading to outflow. What you can show from simple considerations that I won't go into is that the outflow can be shown to be equal to the Alfvén speed. Parker and Sweet showed this. And furthermore, that they're related to each other by a very simple equation, V in by VA as 1 over square root of S, where VA is simply the outflow velocity. S is the Lundquist number. L is the length of the system. VA is the Alfvén speed, and eta is Spitzer. This is the well-known Sweet-Parker model for most astrophysical systems and heliophysical systems. As I said, these are collisionless systems, so eta is extremely low. S is very, very high. The reconnection rate is tremendously low and falls off as the square root of the Lundquist number, so low, in fact, that in solar flares, which happen of the order of a few minutes to an hour, you cannot explain the reconnection on the basis of the Sweet-Parker timescale at all. And so attempts to produce faster timescale has been the holy grail of fast reconnection theory. And one of the really interesting developments that have implications for the particle acceleration problem has been the development that has occurred over the last decade or so, known as plasma instability theory, that I want to talk to you about. And here is an attempt of, it was done by Yimin Huang, who's a colleague in my group, published in our paper in 2009. And what you're seeing here is an attempt to simulate a two-dimensional plasma in which you have oppositely directed magnetic fields. And the picture that I'm drawing here is that of the current density that is built up. And you will see this extended current sheet form, which is very Sweet-Parker-like, but see what happens when the Lundquist number exceeds a critical threshold, which is 10,000 in this case. What you find is this thin current sheet breaking up into many, many bubbles called plasmoids or magnetic islands that go through this process of coalescence and merging and going through a very, very impulsive phase until the entire flux in the system is completely chewed up. This is the plasmoid instability, and what it did was to change Sweet-Parker theory, whereas Sweet-Parker theory is in fact a very good theory below a Lundquist number of 10,000. When you cross that Lundquist number, what happens is that the sheet is not stable anymore. It becomes very unstable. Even if it were quasi-time independent, it becomes very time independent. And if you actually calculate what the reconnection time is, whereas in the Sweet-Parker model, it increases as S to the half and keeps increasing, which is what makes it unrealistic. It turns over. In the presence of the plasmoid instability, and the reconnection rate now becomes 0.01 VA, independent of the Lundquist number. Now that's an important finding, that resistive MHD theory actually gives you a reconnection rate because of the plasmoid instability independent of the Lundquist number. But resistive instability theory is not the only place where you see these plasmoids. Here I'm showing you results from a so-called Hall MHD study, which also shows the production of plasmoids, and particle in cell studies also showing the production of plasmoids. So independent of the collisionality regime that you have, you will have thin current sheets breaking up into plasmoids. And the reconnection rate that you get in collision-less systems is actually higher than in resistive MHD system. It's more of the order of 0.1 VA, which brings it very close to what is observationally needed for flares, CMEs, and often magnetospheric substorms. And this is really a multi-scale problem. What you have is, on the MHD's timescales, if you look at solar things, you're looking at timescales of 10 to the power 5 kilometers. But if you look at the kinetic scales, those are breaking up too. So no matter what level of refinement you go to, you find the plasmoid instability. And one of the things that was put forward by Drake and the Los Alamos group, like Van Gool and others, is that in the presence of islands, these islands can expand or contract. So think of the Fermi process of island expansion and contraction, where you're going through jaws, going back and forth, trapping particles and accelerating them. Now, in the good old picture of reconnection, you had thin current sheets with very, very intense parallel electric fields that could accelerate particles. That's called direct acceleration. That is still there. But what these islands do, they are actually much larger in size. And through a Fermi-like mechanism, they can actually provide a much more important source of energetic particles, especially electrons. And so you're seeing the old Fermi mechanism re-implemented again, but now in the context of these large islands. And why are large islands attractive? Because they're usually much bigger than the thin current sheets. So the number of electrons that you can accelerate by this method are actually much larger than the reconnection layers itself, which can produce very high acceleration, but not enough in number. For those of you who've kept up with RESI data that Bob Lynn and others pioneered in, what you find is that when you have a solar flare, you often have half of the electrons in a plasma volume accelerated to very high energies. And if you just left thin current sheets or Parker-like sheets to do the acceleration, first of all, the rate is not high enough. Second of all, a thin current sheet doesn't have too many electrons. You will never understand the numbers problem. The islands allow you to get to the numbers problem. And I don't have the time to show you some beautiful results. I mean, you see tremendous amount of these magnetic islands, not just in the solar corona, but also in the Earth's magnetotail. This was done by Li-Jun Chen et al. When she was a postdoctoral colleague of mine. Cluster spacecraft sampled magnetic islands in the Earth's magnetotail. And here is Li-Jun's plots of electron flux against density. And what she was saying is that you have 10 islands within 20 minutes, and if electron bursts and density peaks, one of the things that she pointed out is that these islands can have enormous energization, nearly all channels that you look at. And there are some small, you have some small energization occurring at the X points, but at the islands itself, macroscopic features, you have a lot of energization going on. So is it true in the post-GME current sheet? There was a beautiful illustration that Professor Chu showed you yesterday of in the post-flare current sheet, you have these sorts of bubbles. Now we don't have magnetic field measurements to conclude that these are magnetic islands, but it's plausible that these are magnetic islands which may be producing some acceleration peaks. And what's really happened in reconnection theory is that we have competing mechanisms, and we are now beginning to understand through high resolution simulations how particle energization occurs. And it's very, very hard to do realistic collisionless simulations. So people in astrophysics or space physics, particularly in astrophysics, are actually doing a problem that is very interesting to them, but is much easier to simulate, which is the electron-positron plasma. So instead of the proton, where ME over MI is 1/2000, you have the advantage that ME over MI is 1. And this is very important for pulsars and other systems where you spontaneously create electron-positron plasmas. And here you're seeing such an electron-positron plasma simulation done in 3D. And what you're really finding is that the plasmoids become flux ropes. They overlap. Field lines become stochastic. You develop turbulence in these systems, which actually are pretty effective in producing particle acceleration. You start out with Maxwellian type distribution functions, and these are relativistic simulations done. We do not have such comparable simulations, such large simulations with ME over MI of a hydrogen plasma as yet, but what you, and these are all relativistic. Believe it or not, relativistic plasmas have certain simplicities. Their velocities are all close to the speed of light, whereas non-relativistic plasmas are much harder to solve, both analytically and computationally. But some lessons are coming out of fairly interesting 2D and 3D PIC simulations out of the Los Alamos group. And what you're seeing here is the relativistic energy developing long tails in 2D as well as 3D being shown. So my conclusion slide is that 2D and 3D kinetic simulations for relativistic magnetic reconnection, it generates flux ropes, generates strong particle acceleration. You get power law distribution in the relativistic limit. In the non-relativistic limit, this is still a problem that is being worked on, and you get power laws under some conditions. The injection problem is quite serious. And then there are conclusions that support Fermi acceleration mechanisms. And these qualitative mechanisms seem to be robust, but how they show up in different plasmas varies from system to system. Let me stop at that. I apologize for speaking of speed in the last 15 minutes, but I wanted to tell you that magnetic reconnection is beginning to play an important role along with shocks and turbulence as an important mechanism of particle energization. Thank you very much for your attention.
Okay, thank you. Yeah, I think we probably should, because I'm seeing some of our panelists show up. We should probably basically take a break and allow questions during the break. Sorry about that. So you don't get a break
myself that I went over.
But why don't we get back here at 5 minutes past, so 35 minutes past the hours, 9:35 Mountain Time. Give everyone a 10-minute break, and then we'll start our panel 5 minutes late. Is that okay?
I apologize, folks. I didn't have a watch in front of me.
No. I told you to end there. And we have, we're always a little bit behind time because it always takes a little longer. But can you see the hands now?
I will stop sharing and I will now go to the hands, which I can now see. Yes. So I don't know in which order they were raised, but
Jeb's has been up for a long time, either because he's always had a question or he forgot to lower it from some earlier time. So
let me ask Young. Yeah, do you want to ask me a question?
Yeah. Oh, thank you. Yeah. Let me show my screen first. Okay. I wanted to ask about the perpendicular velocity. So in your slide, the perpendicular velocity is given like this.
Yes.
So in cylindrical coordinates, there might be dotted row. But I think the
VPERP has two components.
Okay.
Sorry, if you write things out, the two components are rho dot square plus rho theta dot square or phi dot square. That's your, so this expression that you have, yeah, this expression is correct.
Oh, right. Okay. But I think this perpendicular velocity is different with this. No, I don't know.
No, in my coordinate system,
yeah.
VZ square is V parallel square.
Right.
So VZ square is Z dot square, and VPERP square is X dot square plus Y dot square.
Right.
In your coordinate system, that's the right answer.
Okay.
So it all depends on the coordinate system in which you express it. This expression is not correct.
Okay.
But this expression is the bottom one. One exactly. That's correct.
Right. Okay.
Dimensionally and otherwise. Okay.
Yeah. Okay. Thank you. Yeah.
Okay. Next question from Milo.
Yes, Amitava. So I think it was Dana who a few days ago said that at the X point during a reconnection, you don't have energization of particles. So I was wondering, since you showed some data in these islands on your slide 37, I think, and you showed, you said there are several X points in those measurements, how those measurements agree with that statements that says no particles get accelerated in X points?
I must say, if Dana is on, it would be wonderful to hear from him why he said that there is no acceleration at the X point. Dana, are you on? No, he had to go.
In a break. Okay.
So I didn't hear him say that. with respect, there is an E parallel at the X point. Now, let me, but maybe he's talking about a null point where there is no E parallel. I now understand what he's saying. See, in many of this system, E parallel by definition means E dot B. But if the X point is B identically 0, then by definition, E parallel is 0. But but if you have a guide field in the system, like a magnetic field perpendicular to the plane of the paper, then even though the perpendicular magnetic field has an X point, there is a guide field that is going through that magnetic field. It's not a pure null point that will have a non-vanishing E parallel and particles will accelerate. So what Dana must have meant is a field null where B is identically 0. Then of course, by definition, E parallel dot B has to be 0. So in that case, my system would be, my statement would be, take yourself infinitesimally away from that null point. You have a little B support, you'll get E parallel.
Yeah.
Any other question? There is definitely. There, do you have a question?
So the question is from the book actually. So in the book, as far as I remember, it is written that Liouville's law, I think, is referred to the phase space, but I have a small thing because what I read at that Liouville's law is actually from gamma space. I forgot the actual name of the gamma space, which is not the phase space. So is it
No, you're right. No. Actually, both statements are correct, and let me explain. What I worked in is what you would call mu space. If you take a statistical mechanics course, there are two types of spaces that are introduced.
Yes.
One, which is gamma space. If you have n particles, then that gamma space has 6 n dimensions.
Yes, true.
And then the system is a point in that gamma space.
Yes.
If you go to mu space, which is a space I was working in, where every particle has an R and a V. So if you want to put n particles in a mu space, it becomes a cloud.
N dots.
N dots. And let's say that's a cloud of particles, n dot.
Yeah.
When that particle moves, from conservation of particles in mu space, the velocity and position coordinates will change and that cloud would deform and everything.
Yes.
But it's measured as dx dv, volume in phase space is not going to change. That's Liouville's theorem in mu space.
Okay. Actually, I thought that in mu space, that is the Boltzmann's theorem, because Boltzmann's theorem also is kind of Liouville's law.
No, there's one difference, which is that Boltzmann can scatter particles out of the volume you have. So if you have, I'm sorry, I'm talking about mu space now. This particular cloud thing that I told you, it just deforms and moves around in mu space, but no particles are coming out or going in. That is assuming no collisions. But if you have collisions, then the statement I just made to you is not correct.
Okay, so Liouville's theorem is collisionless case.
In the mu space, in the mu space. In the gamma space, this is a deeper issue. In the gamma space, when you go to statistical mechanics, basically there is another version of this mu space, of this theorem that I'm talking about, which also remains true. Maybe we can talk about that offline sometime.
Yes.
I'm happy to share with you because maybe I could show you some equations and see if there is any other thing.
Sure.
And I can talk about it, yeah?
Yeah. Okay, thank you, yeah.
I see Vrunda doing thumbs up and Satabdo doing thumbs up. Are these questions? No, I see these are
Those
people.
may have been left over from a previous question you asked with a thumbs
Okay.
up and thumbs down.
What a shame I didn't have enough time for questions.
No, I know. And actually, at this point, maybe we could take one more very short question, but otherwise, Nick, are you gonna? Do I turn this over to you and you can introduce our panelists?
Yes, that would be great. But we can take one more question.
One more short question.
Actually, I don't think there's any other.
Well, you get to choose between Savas and Siang Yip.
Oh, really?
No, wait. I think Siang
has this question answered.
Oh, sorry. Yeah.
Yeah. I have answered all the hands that are up. They've not been lowered.
Oh, okay. All right then. I guess. Thank you, Amitava.
I think Savas is making what about me signs.
Okay. Yeah. No, his hand has been up.
Yeah, you have enough time now, but I can take it later if you want.
No, go ahead. Shall we take a question? Do we have time for a question?
Are you going to be around for office hours?
Yes.
Okay, great. We'll do it then.
Okay, thank you.
Great, thank you.
Thank you, Amitava.
Okay, great. So we have Lika. Is Lika here? Yes, Magdalika is here. Yes. So hang on a second, Lika. I want to give a little bit of instruction and tell people what is going to happen, and then we'll introduce everybody. So first off, so in this session, we have invited several young to mid-career professionals in space physics. I know Claire cringes whenever I say mid-career, but
rude.
But you know, it's time goes on, and to talk about their experiences in space physics. They have they'll introduce themselves, and I've chosen them because of they do a variety of things, a variety of different roles in the community. As part of this, I wanted to collect some questions. I didn't do a great job of giving some instruction, but I did put a Slack channel with career panel questions on there. If you want to post them there, you can as we're discussing things. Also, or you could post them in the chat, whichever you find easier. And I will try and go between the two and pick and choose. There's always way more questions than there is time to answer them. But the first portion of this, Lika is going to give a short introduction, and then we'll go to the panelists for about an hour or so. But then in the last portion of this, I'm going to send the panelists along with some of the lecturers that we have into the breakout rooms, into different breakout rooms. And while this is going on, our multimedia support, Brett, will be turning you all into co-hosts so you can move between room to room. Now, as co-hosts, you have extraordinary powers. Please restrain yourself from using those extraordinary powers, okay? Like ending the meeting or deleting somebody, all right? So just as a warning, you will be able to move from room to room, and we'll give you that instructions on how to do that when the time comes. All right. Great. So I think at this point in time, I'd like to turn it over to Lika, who would like to give a introduction to what we're referring to as the Karel Schrijver Career Panel.
I guess it's still good morning here from where I sit. Wonderful session, another day. And a lot of this is possible because Karel Schrijver actually worked hand in glove with me over these past 20 years to make heliophysics what it is today. And a lot of it is actually teaching and training the next generation. And Karel's own personal career actually is pretty exemplary in that it's not the traditional format of getting a PhD and then joining an academic institution or, kind of one of those national agencies. His career moved around quite a bit. And he was going to be here, but he's not. So what I thought is that I'll capture to you in his own words, kind of his thoughts and perspective on his own career, but also some guidelines for all of you. So let me start reading what Karel sent to me. My interest in astronomy has its roots in the series of Apollo missions. I was 10 years of age, glued to the television, in parentheses, at odd times in the evening and the night growing up in the Netherlands, and struggling to grasp what was being said in English and what was going on in space. But going to university to pursue that professionally was not an obvious path. I was the first in our extended family to obtain a higher degree, stimulated by my parents and my high school's teachers. First majoring in physics, but soon switching to astrophysics. I was incredibly fortunate with a series of great mentors. My thesis advisor that many of you might know, Kees Swan, who always emphasized connecting things to the bigger picture. My first postdoc advisor, Jeff Linsky, it's kind of funny, I worked for Jeff too, who taught me, but I didn't know Karel at the time, who taught me about survival in the competitive US arena of science, and Alan Teitel, who instructed me in the US political and funding structures, as well as in leadership. My desire to work on magnetic activity of sun and stars always guided my choices, but sometimes reality just would not cooperate. My first postdoc was to be in the UK, but was waylaid by changes in the laws of working abroad when of military age. But that brought me to the US the first time. And my first permanent position and professorship in Germany did not happen because someone decided that I simply had the wrong nationality, which led me to joining Lockheed Martin. So it was a mix of choice and chance that gave me the opportunity to work on some of the most exciting instruments in solar physics, TRACE, SDO, and IRIS. And whereas my grade school teacher thought I had too many interests to succeed even in high school, in retrospect, I think it was exactly that quality that helped me be a successful scientist. And I would emphasize that that is triply true for all of you young kids. It was that broad interest that guided my professional career from cool stars to the sun, into the heliosphere, and into heliophysics and space weather. I've always lived for exploration, insights, and connections, eventually leading to the Heliophysics Summer School and the textbook Principles of Heliophysics. My popular science books, Living with the Stars, and One of 10 Billion Earths, and even my venture into science fiction with the recently published Immersion, A Career in Science is challenging. Employment, never certain, and willingness to move around required, but it is wonderfully rewarding to discover these things, spot connections, and deepen understanding of the universe around us. And he has some guidelines that is going to, I have to go to the next page. Bear with me just a second while I pull that up. sorry, didn't think it would take this kind of maneuvering going between different systems. So he says, treat whoever you interact with respect and dignity. These are his lessons and guidance for all of you. And learn from their viewpoints. Respect the time your audience gives you when you give a presentation. Treat it like a performance, well practiced and timed, just as actors, musicians, or other stage performers would. And Karel, I know, just perfected that. No matter how difficult a referee or reviewer may seem, carefully consider the advice. These colleagues generally mean to help you by pointing out that something can be improved about your methods, analysis, or presentation. Keep your horizons broad, even though you will feel out of your depth as you dive into a new area. New discoveries often lie at the interface of the disciplines. Be guided by intuition, but work your logic hard. Do not move away from a situation that makes you unhappy until you have worked out where you would like to find yourself. If your desired next job slips by you, consider that in the end, you may find that new paths present themselves. Share your knowledge and your data. There's plenty to discover in the universe. And finally, collaborate with colleagues and support your community. Working in teams increases your expertise, gives you visibility, and offers access to new perspectives. From Karel Schrijver. Thank you.
Thank you, Lika, for sharing that with us. All right, so what I'd like to do is move on to our panelists, and I'm going to have them introduce themselves. So the first thing is to tell us who you are, where you are, and I've asked them all to find, I don't know, I didn't confirm that they were able to do this in time, but I've asked them all to find an object to share with us that they have handy. So is that, I don't know if that's a surprise, or I see everybody sort of reaching over to grab something. Great, okay. So Hazel, why don't you start us off? Just tell us who you are and physically where you're located right now.
Okay, I'm Hazel Bain, physically located in Boulder, Colorado, and I work at NOAA Space Weather Prediction Center, but also CU Boulder.
And what do you want to share with us?
I've got my climbing harness, which is not getting used very much at the moment. Yeah, I think the gym's open, but I'm not quite ready to be climbing where everybody else might be sneezing. So.
Great. Andreas, could you do the same?
Yes, can you hear me?
Yep.
Okay, awesome. I am in the Millennium Falcon, as you can see. And no, I'm just kidding. I'm in Boulder, Colorado as well. I'm part of the Southwest Research Institute. And the object that I wanted to share, well, okay, that took me by surprise. But luckily, I always have in my desk a pair of bongos. So there they are.
Perfect. Thank you. And Claire.
Morning, everybody. My name is Claire Raftery. I'm the Director of Education and Outreach for the National Solar Observatory, which is also in Boulder, Colorado, but with a new site in Maui, Hawaii. Hopefully some of you saw the new de-kissed pictures earlier this year. I am physically located today in my house in Louisville, which is just outside of Boulder. And I wanted to share with you my pilot's logbook. It doesn't have many flights in it so far, but this is the goal once we are allowed to resume lessons again. So this has been a lifelong dream of mine that I've been working on for the last little while.
Okay, great. Thank you. So now we have the elevator speech exercise. So let's go backwards. Let's start with Claire and we'll work our way back.
Elevator speeches are always the worst, aren't they? Okay, so as I mentioned, I'm the Director of Education for the National Solar Observatory, and the objective of my work is to bridge the gap between complex science conducted by the observatory and whoever is my audience at the time. So whether I'm communicating to the general public, congressional representatives, or children, my work focuses on finding connection between the audiences and the work done at NSO, and then walking them through the concepts in approachable bite-sized ways. I use a combination of analogies, stories, demonstrations, and models to accomplish this, and I consider myself sort of a science translator. And as a result, my background in solar physics research is immensely useful as it allows me to communicate effectively on both sides of this communication gap.
Great, thank you. Andres?
Okay, I'm a senior research scientist at the Solar Research Institute. I am working a lot on, I'm also very heavily involved with the Frontier Development Laboratory. And in this moment, I'm focusing on trying to bridge the gap between deep learning and machine learning and heliophysics. So a lot of what I'm doing right now is like act as that nexus between the science applications of machine learning and the commercial applications of machine learning, which have different requirements and different kind of constraints.
You're also going back and forth between the two events going on. I am a bit distracted.
Great, thank you, Andres. And Hazel.
Okay, so like I said, I work at the NOAA Space Weather Prediction Center. So a lot of what I do is it's interesting, all three of us are at the joining of several different disciplines. So what I do is very much at the edge of like research, but also moving that research into an operational environment where forecasters can use this science that the research community is developing to understand phenomena in the heliosphere and use that to sort of forecast space weather impacts at Earth. And so my job is trying to work that part in the middle where we're taking the research and trying to make it into these forecast tools that the forecasters can actually use. So specifically, I work a lot on radiation storms, so SEP events, trying to forecast them for things like human space exploration, and also for civil aviation to give advisories for a new initiative that we started, which is to give advisories to civil aviation to sort of give them a heads up of what their elevated radiation levels might be during a storm. So that's the main focus at the moment.
Great, thank you so much. All right, so to begin with, before I get to the student questions, I have one or two questions that I like to ask. So one of them is, what was either the last nexus point, the last sort of decision point in your career, or the most influential, the one that the most interesting decision point in your career that has come up? So either the last one or the most influential. And we usually kind of look around at each other and somebody takes it, but I guess I'm just going to have to call on somebody. So I think we'll start with Claire on this one.
All right, I think that's because you know my answers for the most part. It's cheating. So there have been a few nexus points in my career. I think I will pick the one that was probably the most transformative for me, and that was when I decided to officially stop my career in solar physics research and commit myself to education and outreach full time. And that was a surprisingly difficult decision for me. So even though I'm definitely happier in education and outreach, and even though I'm much better suited for this career, the stigma attached to that at the time was quite difficult to work through. So when you are in research, there is this sort of atmosphere that why would you do anything other than research? This is the, the quintessential be all and end all of everything. And so it took me kind of a while to be okay with the fact that I was pretty good at the outreach and communication and education side of this, and it made my soul happy, and it made the people around me happy because I was in a better frame of mind. And so that was absolutely the best decision that I ever made, even though it was a very difficult decision. And it's interesting because there's still sort of knock-on effects of that, where again, a lot of my colleagues that I knew in research assume that I am in outreach because I couldn't make it in research, as opposed to because I made an active choice to change my career path to do something that I was much happier doing. And so it's a kind of an ongoing stigma battle that I continue to fight, but it's one that is totally worth it for me. I get immense satisfaction and pleasure out of doing education and research, or education and outreach, and working with students and members of the public, and going to Capitol Hill and doing all of those kind of fun and interesting experiences. And especially because I get to be quite creative in my work. I get to do a lot of interpretive type of work in doing what I do. So it constantly keeps me on my toes. That's not to say that it's a walk in the park and it's always very straightforward, but it is generally I'm better suited to me as a career. I think that would be my big nexus point.
Great. Choose one of your other fellow panelists to respond.
I will punt to Andres.
Okay, I think that.
Oops.
Frozen.
The Millennium Falcon crashed. Oh no.
I guess
The latest in my laboratory. Okay, I'm here.
Okay, great.
I'm back. Sorry, long distance superluminical communications are pretty difficult. So I think the nexus in my career, the last nexus in my career, was my involvement with the Frontier Development Laboratory. Because it is a program that is meant to be is very diverse in terms of the expertise that it pulls. It's a program where you bring people from academia, industry, machine learning, and domain scientists to work together to hack at a problem for about 2 months. And that requires a lot of things that I have never been taught, especially when it comes to leadership. I have been leading teams for 4 years now. This is my 4th year leading teams there. And so learning how to create a common language and fuse a very diverse team in all aspects is something that I have discovered to be fascinating. And I believe that what the FDL is in terms of an experiment in team management, team building, and interdisciplinary research is potentially incredibly disruptive for science. And for me, that's, I think, the most fascinating aspect of it, because everything that I'm using in the Frontier Development Laboratory is not only scientifically super stimulating and exciting, but I think also can completely shape the way I am planning and assembling and building the team that I want to create in Southwest to just disrupt the way we do research.
Hazel?
It's me. Okay, so probably again a similar thing, like a big move. So I feel like there's nexus points every 6 months, but I would say the most transformative one was my move from UC Berkeley over to NOAA Space Weather Prediction Center, just because it was a completely different job. And that again was like a conscious choice, partly because it was going from soft funding, doing a lot of proposal writing at Berkeley, and that was quite stressful on a visa, to be continually having to source the money to make sure your job was there. And I found that I just wasn't getting a chance to like dive into problems quite as deep as I wanted to. Whereas at SWPC, we're more, the funding is sort of more secure. I don't have to write proposals if I don't want to. And I think it gives me an opportunity to sort of dig deeper into problems, and it gives me an opportunity not to have to think of a good idea based on a deadline, but to let those things kind of grow naturally. And I also I had been working on some instrumentation projects at Berkeley. So to go from instrumentation over to space weather seems like kind of a big switch. But I think what I'd learned from the instrumentation side of things is I really enjoyed the applied science side of things. So for GRIPS, I was working on a lot of like the ground support software, handling the data, moving around, that sort of thing. And I just really enjoyed it. The code that I was writing actually being used for something. And that's very much what we do at SWPC. It's very applied in the sense that what we're doing will get used the minute it gets released into the forecast office, and it's going to be applied to something that has sort of tangible effects. So those two things were the big transition for me, going from soft money to being more supported, but also this idea of going from sort of doing something that maybe only a small fraction of people cared about to doing something that was easily applicable to a whole bunch of industries around the world.
Okay, great, thank you. So I'll start to go to the student questions now. So, and if you've got questions, I've got a list already on the Slack channel. If you've got new questions that you haven't posted there, you can post them in chat, and we'll try and feed them in, and people can bounce ideas off of each other. I think this first question is just related to what we just discussed. So if you want to add anything to what you commented on, the question is, what circumstances led you to switching your research topic or the focus of what you're doing at any given time? And you know, we'll open it up for a free-for-all rather than calling on people. If just unmute yourself and start talking, and we'll duke it out if need be. Hazel has unmuted herself.
It's the global sign these days that you want to say something is the mute button. Honestly, a lot of decisions come not necessarily from planning, but from opportunities that arise at a time. Like, I think that you can plan, and then something will just come up that's too good an opportunity to miss. And so you take that chance when you can. So I would say opportunity, maybe rather than necessarily active planning.
Sorry.
Go ahead, Andres.
Andres.
Okay. Let's the really quick. I want to say that for me, I mean, opportunities, it's a very important component too. So there is a component of randomness to the thing, but I think that for me also, for example, in this case of the last nexus that I mentioned, there are problems in research and in science that you become aware of that remain unsolved for a very long time, and that people have been trying to solve them in many different ways, but not in a completely satisfactory manner. And sometimes these opportunities present to you by chance, but the fact that, and in this case for me, particularly is machine learning. And so these opportunities present themselves where you suddenly realize that these problems that you have been trying to solve for a long time, there is this opportunity that allows you to tackle them in a completely different way. And for me, that was the case. And so what I want to highlight is that there is a component of chance, and there is a component of kind of like priming your mind for what you want to do. And it's when those things combine that you can take those quick pivots, things that we're not expecting, but you're like, oh, okay, this aligns with some of the things that have been bouncing on my mind for the last years or whatever.
I agree with both of those, that opportunity is definitely a really important factor, and to kind of keep your eyes open for opportunities as they come around. My experience was slightly different. I had been a little restless in my research career. I was doing okay in research, I was publishing papers, I was doing what you're supposed to do as a researcher, but I didn't feel like I was necessarily fulfilling what I was supposed to do. When I was a graduate student, I had worked in various forms of science education, kind of inadvertently by accident. So I worked in a science and art museum as an explainer, and I worked in an after-school program as a tutor for kids with dyslexia. And I realized as I was going, kind of advancing into my research career, that I got more out of those experiences than I was out of writing papers. And so I didn't know where I was going, but I knew I was looking for something different. And so I started talking to people and asking them, and I didn't know that education and outreach was a career at that stage. And I was speaking to a friend, the girlfriend of a friend of mine, and she pointed out that there was an entire department dedicated to the thing that I was aimlessly searching for just down the corridor from me that I had never heard of before. And so I started out by just doing some volunteer work with the education and outreach group at the lab I was in, and then very slowly increasing my participation until I realized that, yes, this was the right path for me. So there was some opportunity in that I spoke to the right people at the right time and they were able to point me in the right direction. But there was also I was actively searching for something different. And I think because my nexus was quite a left turn to a degree, I think that probably required a little bit more sort of actively seeking ways to change and not just waiting for opportunities, because it was unlikely that those opportunities would have crossed my path, even though they were only based down the corridor from me. But that's a story for a different day. So I think a combination, like Andre said, a combination of knowing where you want to go and what is important to you, and then positioning yourself to be ready for that. So whether it's trying to participate in projects that allow you to develop those skills, or looking for partnerships, or doing things in your spare time. You know, sometimes to get to where you need to go, you've got to put in the outside work in order to get yourself positioned to make that leap when it comes along.
Okay, great. Another question. What is are there any standard young researcher mistakes from your experience that people should be looking out for?
I think we need alcohol for this question. Yes, I think is the answer.
Therapy, if you want.
All right, so some mistakes. There's many, I think, that you can make. Pick one. The one I will focus on, I think, is not how to phrase this. Not surrounding yourself by the right people. People are a really, really important factor in the success of your career. And I think when you're a junior researcher or a less experienced person in the field, you don't necessarily realize how important that is in the long run, because you don't know any different at that stage. And this also ties into the importance of mentorship and so on. But I think being able to look backwards and realize the importance of having people around you who can advocate for you, who can put you in the right positions, who can put you forward for things that might make you uncomfortable, or that you may not be on the top of somebody else's list for, but because somebody who is at the top of that list is saying, well, no, you should have this person, and people who are going to be supportive of you. Like, research is hard. It's a tough world to be in. Sometimes it's frustrating and it's stressful, and so people that will support you in the hard times as well as the good times, I think is something. So I think to flip that around, I think the mistake is focusing on perhaps on the institution or on the research project or on the topic, as opposed to the people who are at the institution or the people who are leading that research or something like that. And then, you know, following the humans as opposed to the reputation.
Great.
Does that make sense?
Other traps or mistakes to avoid?
I just want to resonate with what Claire said, because it was fascinating when she was like, so many, I don't know. And I was thinking, networking. And she was like,
sorry for stealing your thunder.
No, you didn't steal my thunder. I just think this is so important and it's never given enough. And that's what I want to do right now, just highlight that. Because I think that the mistake, I mean, science is an extremely social endeavor, more so than anyone ever believes or understands or is trained for. And the social aspect of science is something that you should pay attention and be mindful of. People say, I don't like politics. No, but you don't like politics done corruptly, or you don't like politics done like backstabbing, Machiavellic way. But you have to talk with people, you have to interact with people, share ideas, and all this is very important. And I think the mistake that I see a lot of young people make is that they don't realize that they have to be mindful in the way they do networking. And choosing definitely your institution is one of those things. But also, if you go to a conference, you have to put yourself there, and it's not comfortable to meet new people, and you need to bring like experts in your field to your posters, and these kinds of things are hard to do, and a lot of people don't do them and don't put like mind into it. So that's I think the mistake. The mistake is not making sure when you meet new people, when you meet new people at all stages of their career. This is very important. You are also working, and so that's I think what I wanted to highlight, that it resonates strongly with what Claire said.
Both of those, I would absolutely agree. And I'm terrible at talking to new people at conferences. That really, I'm just not that comfortable approaching someone I don't. So that's definitely a learned skill that you have to do. But another people-related thing is, I would say, is not reaching out for help. I know that we all have this thing where there's this attitude of like, maybe I need to solve the problem myself and I can't ask for help because it'll make me look stupid. There's an absolute element of truth in that. Like sometimes there's a lot to be gained from like, you know, digging down on a problem and just taking a breath and trying to solve it yourself. But there's also a lot to be lost in terms of time, in terms of collaborations and stuff, just by trying to solve it only yourself. I mean, I think Google has the whole, is it Google that has the whole thing? Like only if you're stuck on a problem, wait for 30 minutes before you go and ask for help or something. I mean, there's a reason that they're a big, you know, company and have policies like that, but, and maybe not 30 minutes, like some things take a bit longer than that to figure out. But I know that I'm one of those people who won't necessarily go and ask someone for help immediately, and I'll maybe struggle with a problem for longer than I should have. And I think I've probably lost valuable time over the years from doing that, where I could have sent someone an email or, you know, gone next door to ask someone in the next office or something, or nowadays calling someone on Skype or Zoom or something. But yeah, I think there's a lot can be gained, and sometimes people come up with a completely different solution than what you would expect, or they'll ask you, and often people don't even solve the problem for you, but they might reframe it or ask you questions to try and get you to explain it in a way that suddenly makes you realize, oh, I've missed something here and this is how I should solve the problem. So yeah, just not sitting on your own trying to tackle a problem for weeks on end. Sometimes it's better just to reach out.
Okay, great. Question along the lines of networking. So how, advice on how to do networking and gaining a mentor without feeling manipulative. So maybe this speaks.
Manipulative.
Maybe this speaks to Hazel's uncomfortableness, and maybe Andreas's plea about, you know, politics isn't always Machiavellian.
By manipulative, you mean like to sort of, when you're asking someone to mentor you, or to go and network and things?
Liz, you wanna?
Sure. This is just a hang up I've had for many, many years, because everyone I talk to is always like, network, talk to people at conferences. But it always felt very one-sided, like you are using them in the relationship or in the conversation, which just makes me feel very uncomfortable. So if you have any suggestions on how to do it in a way that is more like collaborative instead of one-sided.
So maybe not, a couple of things come to mind there. One, I actually quite like it when someone comes and talks to me, because it means I don't have to go and do the introduction. Which I think you need to remember that there's humans on the other side of this interaction too. So I think that is fine. And sometimes you might catch someone by surprise, but don't like, and I've definitely done that where I'm like, hello, and they're like, oh, because I think sometimes we're just not used to people coming up to us that we don't already know. So I think that's fine. Just give them a chance to like settle into the conversation. Two, I would say, I have, and this is a sort of a story rather than a piece of advice, but I absolutely interrupted the wrong people at the wrong time and found myself just being like, oh my God, I need to get out of these conversations. That's okay too. Like, you know, I've gone up to people and been like, oh, hey, how's things? And they're actually in a conversation and I'm like, you know what? I'll just come back later. Nice to see you, have a cup of coffee, and I'll just kind of slink off. Like, that's trying to get out of those situations gracefully is always a little tricky, but like, again, people are fine. Like, if you were to come up and sort of start to say hi. What they're not fine is if you then sort of hang around standing in the corner just staring at them, waiting for them to finish their conversation. So I think that's just sort of general human interaction rules, you know, just be kind of be aware, but like, you know, say hi. If someone doesn't have time right then, that's not probably about you, it's probably about them. They've just maybe got something going on at that same time as well. In terms of actually mentoring stuff, like I have in the past absolutely emailed someone and been like, hey, I'm having a trouble with this particular thing. I would really love it if we could have a chat, and you know, I see that you have tackled these problems in the past, or that you'd be somebody who could give me some insight on how to progress past this problem or progress in my career. Would this be something that you're open to? And so doing that in a way that I give the person kind of an out, where maybe I'll say something like, you know, do you have time in the next few months to have a chat about something? And it means that if they're just are swamped or whatever, then they could just say, actually, no, I don't have time. So giving that person an opportunity to say, maybe they don't have the time or things are super stressful for them or something, without them feeling bad about that. So that I think does make it a two-way process, where you're saying, if you have time, I would love to chat to you, as opposed to just saying, please be my mentor. So maybe other people have other experiences of that. So mentoring is also can be informal. And I think different people approach it in different ways, for sure.
I would like to add. Oh, I'm sorry. No, now it's your turn, Claire.
Okay. I would sort of riff off what Hazel said, and you know, I both have a mentor and am a mentor at the moment, and it's immensely useful in both directions. And my mentor has told me that she gets a lot out of our conversations as well, and I find myself getting a lot out of the conversations I have with my mentee also. I think what Hazel said about remembering that there's humans on the other side of all of this is really a big important part. Like the people who are at conferences, they have business they need to get to as well. They have people they need to communicate with or have conversations with. And so I think being conscious of why you want to talk to them, and that's another big one, is that the idea of networking for the sake of it is not necessarily effective, and it gets a bit tedious sometimes if you're just talking to people just because, and like, I'll introduce myself and then someday they might give me a job, but I have nothing to say to this person. That's not really particularly impactful. I think it's much more useful to be selective in your networking, but authentic in it. So if you have a paper that you're working on, or if you've just read a paper that's really interesting, or that you are confused by, or you listen to a talk at a conference and somebody said something that you didn't fully understand, that's a great opener. That's a great conversation starter. But to walk up to somebody and to just say, hello, I am so-and-so, and I also do science. Crickets. There's no conversation there. You know, you have to have there has to be something to talk about in order to really qualify having a networking conversation with somebody. And bearing in mind, the more authentic that conversation, the more likely it is that person will remember who you are. I'm like, oh yeah, that was that student that I met last year at AGU, and they came up with this crazy idea that, you know, set me on a different track, or they, you know, that solidifies the interaction, as opposed to you being one of many who just happen to introduce yourself to somebody for no particular reason. So my personal opinion is that it's much more beneficial to have 5 genuine conversations as opposed to 50 surface level conversations. I think also being interested in what the other person is doing is a really important way to network. So, you know, again, if you just heard a presentation or you read a paper or something, and engaging somebody in the conversation about their work, you know, people are people, they like to talk about themselves. And so making sure that that's something that they have an interest in, and that also gets away from that like one-sidedness that you were talking about, Liz. And being able to try and make it more of a two-way conversation. I think one of the things that took me a while to be comfortable with, and I see it a lot with the undergraduate students that I work with, is that when we're in undergraduate level, it's very hierarchical, right? So it's the students and the professors, and there's this huge divide between them. As you go through graduate school, that gap closes, and by the time you graduate, really everybody is on a level playing field. And I think remembering that fact, that you are these people's peers now. They are not your superiors, that you have just as much right to be in the room as they do. So you bring something to the conversation as opposed to expecting them to carry the conversation and you just absorbing, like is more typical in an undergraduate situation. So I think just trying to, you know, instead of networking for the sake of it, don't think of it as like a chore. Think of it as an opportunity for conversation and to get to know your colleagues. And I think that might shift the perspective on it a little bit. And
Quality,
definitely
not
pick your
quantity,
moments. Right? Say that again.
Quality, not quantity.
Yes, quality, not quantity. And
If
pick
you
your
have,
moments. If you see the person that you've been trying to talk to all week and they are deep in conversation with somebody else, this is not your time.
It's true. And it's one of those things you said, like 5 conversations. If I come away from a conference with one good connection, I feel like I've done well. Like, and I mean a really good connection, something that like might actually grow into something. I don't try and put too much pressure on myself to know everybody every single time, every time I go to a conference. Yeah.
We talk about networking as if it's a, you know, a tool or something. It's really just the business word for a human interaction.
Yeah, I would like to add that there is also another component to this, that is that you pay forward. So there is going to be someone as you go through life, and people help you with advice and with insight and they extend their networks to you and things like this. Eventually, you will be in a position to do the same for another person, and so that also helps. I mean, that is kind of like what I say, politics don't need to be Machiavellic. You can be thinking about how to also have a positive impact on the world through your actions and through the way you connect with people, and you leverage those connections. And extending your network, for example, to someone that is just starting is a way of doing that. So that is the thing. The other thing that I would like to highlight is that, yes, people like to talk about themselves. So, and they like to give advice. So that is like, I mean, there is not an easier way than start a conversation with someone you want to get to know, and to get things that you don't know what. Sometimes you don't have any specific ask, but people are happy to tell you about their paths and what take them there. And oftentimes you get a lot of valuable input from that. And in conferences, sure, like it's really hard and kind of awkward to just hang out and see like stalking someone, but you can also just send them an email and say, hey, during this conference, I'm in this conference, and I wanted to ask you if you have 30 minutes because I want to ask you this or that. And people typically say, yeah, sure, let's meet in the next coffee break tomorrow. And that takes a lot of the awkwardness of the whole thing. If you just, and this is also particularly valuable in very large conferences. If you're like in an AGU or something like this, which is thousands upon thousands of people, to have an idea of who is going to be there and who would you like to talk to and why, so that you can send some emails. And people are really generous with their time. So I think that's something to keep in mind.
Great. And I wanted to add that under the current circumstances, networking opportunities are going to be more intentional, right? We can't just say, okay, beer's being served at AGU on this day and have everybody show up and have it kind of be. So it's gonna be intentional and feel a little artificial. Get over it. Right? Because it's important, and we recognize. So we're going to be. I know that I'm involved in starting to organize some of the networking opportunities at the virtual AGU this year, and we're going to have to do this in an artificial way. But it's such an important thing that we're spending the time to organize it and provide opportunities. So please take advantage of those opportunities as they come up. Let's talk a little bit about funding. So one question was just about the ratio of research to, of soft funding to hard funding at your institution. Another question that maybe Clara can touch upon is, types of funding for outreach and what funding is available for outreach, what are your circumstances, and so why don't we start with those two? So Andreas, what is what's the ratio of soft fund? You're at SWERI?
Yes, I'm Southwest Research Institute. I have 20% base salary, and the rest, 80%, I need to bring in. And just to add a little bit to the question, this is the other nexus that I was torn between sharing with you. Like, shall I talk about all my experience with machine learning and leadership, new novel forms of leadership, or shall I talk about the moment where I said, you know what, I'm going to go full soft money for it? And so it can be made to happen. I was very scared. It was terrifying when I made this choice, but so far I'm still here. And ask Karel Schrijver, I don't know if you saw in his text that Lika read, he was also always someone that did soft money all his life. And you're always, yes, with some uncertainty, but it's something you can get better at. And there is always something, like, you're never going to find yourself without options. Even if funding runs dry, you can switch industries, and that I have seen that happen a lot of times. People are always happy to where they are, and in terms of what they do with their degrees and what they do with their expertise. So anyway, I just wanted to bring that up now that we're talking about funding and soft money.
Great. Hazel, what's the situation in your circumstance?
And so until this month, until Andres and I got a machine learning proposal funded, I was 100% at SWPC and like of hard funding. So my job, the requirement is mission orientated. So because we're a FEMA center, because we're a space weather provider, there needs to be a lot more stability, I would say, in our organization than having people come and go because of funding structures of something external to the agency. So almost everybody in fact, pretty much everybody in our group has base funds of some kind or another. So some portion of the research group are federal employees, so they're protected for life kind of a deal. And then there's the contractor side of house, which is people like me who work through CU Boulder, through the Series Institute, and we are a cooperative institute to NOAA SWPC. And so basically, SWPC can't hire feds to do every single thing that they need to do to cover all of their mission critical objectives. So people like me come on board, and that's people all the way from the software side through the research. None of our forecasters are contractors, but I don't think any of our IT support are, but like there's quite a lot of us that are on the contract side. But even then, those jobs are usually tied to pretty stable projects. I think when I initially came on board, I was working for the Discover project to develop new products, solar wind products for the forecast office, and to continually make sure that things are running. So right now, and then I switched more onto the radiation side of things. So right now, the radiation model that's there, it needs to be upgraded. Well, we implemented it last year, but there's upgrades that'll happen as new developments happen. We need to make sure that it's running. So you don't want necessarily different people coming and going all the time, because you need that stability. We don't want to have some big storm happen and to have lost the institutional expertise to fix the code that gives the forecasts. So I would say a lot of it's driven from that perspective. We do have some flexibility to do some research on the side. So that's, as I say, I've got 25% of my time right now is working on a machine learning project for SCP forecasting. But the rest of my time is very much core work towards SWPC objectives for forecast products, and those are things that are being planned all the way out sort of through 2020, well, probably 2034 or something like that, because the next bunch of missions will launch in 2024, and those have sort of 10-year lifetimes. So we're planning things for many years in the future. We're not working on a 1, 2, 3 year cycles, and so yeah, I think we're pretty well supported. Like, so it would take something to happen at a government level for lack of support for space weather for, I think, that to change, which I'm immensely grateful for. And just to say, there are other jobs like that out there for sure. There's other, I think, maybe Claire can talk about this as well when she talks about her job, but maybe she can mention a little bit about NSO. NSO has people who are like more on the service provider side of things. So those to support instrumentation and things, those people are usually more well supported by the organizations.
Yeah, so NSO is funded almost entirely by the National Science Foundation. We do have some small amount of funding that actually comes from NOAA SWPC. Some of our instrumentation is used as input for their models, and so they help to support the maintenance of that. But for the most part, we are funded by NSF, and so the way it works is NSF gives an organization called AURA, which manages a bunch of different observatories, funding to run the whole observatory for the year. And so for the most part, all of our staff are funded from that. There's the opportunity to apply for grant funding, but it's not necessarily a requirement. When things get tight, sometimes that's encouraged, so as we can kind of bridge over difficult years when financially. Our scientists are, let me see, there's two different classifications of scientists. One is tenure track, and I think the other one is associate. I don't remember. But one group has 25% of their time that they can dedicate to their own research, and the other group has 50% of their time that they can dedicate to their own research. This is, when I started working at NSO, I didn't really realize there was such institutions. And I think the way I think of it now is that you basically have a job. Somebody pays you to do a job. And so the folks at NSO are building and maintaining and operating telescopes. And so your job is to do that. And then on the side, you get to do some research, which is a different sort of orientation than in a university setting, which is largely your job is to do the research, and then you might have to teach, or you might have to sit on committees or something on the side. So the focus is different, but as Hazel said, the stability is also quite different. So the funding structure at these service institutes, I feel like, are a little more stable and long term, and that is, I guess, the way to think of it is it's the price you pay, that you have the stability, but you have maybe less freedom to explore whatever it is you want to do. Whereas if you're in a university setting or a soft funding setting, you can apply to do whatever it is that you like. Now, at these institutions, you can also do that. So you can still write grants to do research on different things that you then can bring in funding for yourself. So that's not it's not a hard stop on that. It just means that there's a little more security. So there was a question about my funding situation. I'm fully funded by NSO on their base funds, and as far as the sort of landscape goes, when I worked at the lab before I moved to NSO, I was fully soft funded, and that was somewhat challenging. The funding for education and outreach is not unstable, feels very like a really scary kind of a word, but it comes in waves. So for a long time, the education and outreach world was pretty stably funded by NASA. They had a rule where 1% of the cost of every new mission was dedicated to education and outreach, and they did away with that in, I think, 2014, and that was a bit of a calamity across the field. Coincidentally, that was 6 months after I decided to quit my research career and move into education and outreach, so that was a little bit of a spanner in the works, but we'll talk about that another time. Since then, things have sort of restabilized themselves. The community, I believe, is smaller. I used to be in the NASA sort of education and outreach world. Now I'm much more in the NSF, and there's definitely connections to them, but they're also subtly different. The focus used to be very much on education. It is sort of morphing into communications, which is different, and the education work is being done sort of through different channels. So it's depending on what it is that you're trying to do. I think there's different ways to go about it. So if you are a researcher and you would like to have a program that supports students, or you would like to participate in an existing program and maybe volunteer with them or support, you know, have some small portion of your time, I think that is something that's quite easily achievable. The National Science Foundation is really excellent at supporting this kind of work. They have a whole department called Education and Human Resources dedicated to education grants. NASA is also very good at supporting these kinds of programs, and I think a phone call to a program officer is usually the first step in trying to figure it out, especially if it's not an awful lot of money. So for example, I know a lot of researchers who have NSF grants, and they will ask for a small supplement so as they can hire an undergraduate researcher to help with the program. Those kinds of things are pretty easy. If you are interested in getting into this more full-time or more professionally, like this is your career then, the things are somewhat different. They're still kind of up in the air. I don't know, maybe Nick, you have a different perspective on this again. I know that you're still more active in the NASA education world than I am anymore. I think having opportunities to work at the likes of an observatory or a science museum or an institution like that is a little bit more stable and reliable. One of the questions I get a lot is, what do you need to be able to do this kind of a job? And so I'm assuming you're all pursuing some kind of research career, so that's, I think, a great start. The other thing I would recommend is that you get some kind of teaching experience. You don't have to go become a K-12 teacher, but to, you know, have some experience of standing in front of a classroom and understanding what it feels like to be an instructor of some sort, I think is also very valuable. And that, unfortunately, a lot of that comes through volunteer work, giving talks, working with students, you know, all of that kind of stuff positions you well to be hireable when it comes to these kinds of jobs. When I applied for the job at NSO, the job description was actually 3 separate jobs that they just sort of morphed into a single entity. And because of the variety of experiences that I'd had, I actually met almost all of the qualifications for this job, and that's pretty unusual. But the point being that the more varied your experiences, the more likely it is that you'll be able to mold yourself into whatever the career option might be. So I'm sorry that I don't have a hard and fast, well-rounded answer for this. It kind of goes back to what Andres was saying about opportunity and where do the opportunities present themselves. You know, the job at NSO appeared out of nowhere, and like I said, I met all of the qualifications, and so it would have been silly of me not to apply for it. And thankfully I got it. So had that not happened, I might have been back in Ireland at this stage. So you never know where things are going to end up.
I just add a little point on there that's a little bit of a tangent, but just it is highly unusual for someone to meet so many of the job requirements. And as somebody, so it's something that we're thinking about at SOPSI. We're trying to make sure that our hiring practices are more inclusive and trying to figure out what it is that are barriers to people applying for those jobs. And that's one of those things that we see, that some people think that perhaps they need to meet every single point on a job application in order to apply. That's absolutely not the case. When people write these things, generally they have in mind that someone could come in and they could do a bit of this and they could do a bit of that and they could do a bit of the next thing. I encourage you, if you have even some of the things on those lists, do apply, especially for jobs like at SOPSI. I know that what we do is so versatile, and this comes back to the funding structure idea, like of the idea of the pros and the cons of being at somewhere where you're more institutionally supported financially versus where you're soft money focused. It is about that freedom to be able to do what science problem you want to do. Like if you have a burning desire to understand one physical phenomenon in the world that's not understood right now, probably you're more on the research soft money side. Where my job is you get moved around an awful lot, and it's more kind of, I don't necessarily always have the choice over what it is that I want to work on, but for me I like that. I like being able to be given a problem and to solve it. Like I'm not so attached to, I think my background has mostly been in like solar flares, but I'm not so attached to solar flares that I can't work on solar wind or work on radiation storms or whatever. Like I like just solving problems. So that's that thing. But for a job advert that comes out from somewhere like me, from somewhere or like my job, it would look like you have to have this laundry list of things, and that's really not the case. What they're trying to say is they want to you could work on all these different things and you need to be a little bit versatile. So I just wanted to point out that Claire is exceptionally well qualified, but not everybody will meet every single point on a job advert, and that's okay. We want to hear from you anyway. And I would say that other people probably agree with that. Like, often sometimes we find things in people that we didn't even know we wanted to look for.
Yes, thank you, Hazel. I didn't mean to suggest that I had all of the skills. I meant that it was just a lucky coincidence that I had the, kind of run the gamut with lots of different, dabbling in lots of different things, which was lucky. But absolutely, if you are, even sometimes if you are just interested in a job, that is enough to justify applying. Because if you don't get it this time, you're then showing your interest, and there might be other opportunities that the hiring panel look and like, well, not this one, but actually we have this other position that might be a really good fit for you. So yes, please just apply for the jobs. Don't feel like you have to tick every single box, because often, and this is especially true in the education world, that the people who are hiring the positions don't actually know what they want in the person who's going to do the job. And so that was another example of this job, that the job description they wrote for the position I ended up taking was 3 separate jobs, and that was a ridiculous expectation. And so when I took the position, then I just sort of morphed it into what was a more realistic, actual singular job to do. So the people that are writing the job descriptions don't always know what they're ultimately looking for either. So throw your hat in the ring. You've got nothing to lose.
Okay, great. At this point, what I'd like to do is take a short break. Looks like about 10 minutes. So that would bring us back at 50 after the hour, or 10 of the hour, for those of us on the hour. And when we come back, we'll be switching into the breakout rooms where you can there's still plenty of questions to ask. You've got about a half an hour to talk to people individually, and we'll give you some instruction when we get back. So take a 10-minute break. Be back by 10 of the hour.
Very nice. Thank you, everyone.
Okay, Nick, everyone has been made a co-host. I'm sorry, you're muted still.
Yep, thank you.
No problem.
Great. Thank you.
Sure, sure thing.
And so when we come back and you see where to move on the panelists and Lika and Dana and Amitava to the We're going to have free breakout rooms. Okay, great.
Mm-hmm.
Okay, good. Thank you.
Thanks.
So Dana and Amitava.
Yep, I'm here.
If you find that nobody's got any questions, but people want to hear something, if you go to the Slack channel career panel questions.
Oh yeah, I've seen that.
There's questions posted there from various students. So if you need any conversations, feel free.
Okay.
But,
do you want us to be able to address those questions in this panel, or just leave it up to them?
I think you should leave it up to them, but if nobody's got any questions, but they want to hear more, you know, then you can use those, you can seed those questions.
Okay.
Right.
And this is for a period of 20 minutes, or 11 to 11:20, correct?
It will probably come back. It will